वो वेब कैमरा नहीं मिला तुमको?
Good evening to all of you. I'm Vaibhav Pratap Singh from Syrac, Bangalore. Am I audible? Yes. Yeah. Okay. Thank you very much. So we'll start with the webinar. Today we have gathered here for a webinar to explore the realities and understand the opportunities related to quantum networks. The idea of this webinar. Sir, I'm able to hear a playback.
You are on mute.
So there is a, means I can hear the same sound back. I don't see anyone. I'll continue with the session. Okay. So the aim of this webinar today is to explore the experimental realization, the functioning, the overall network infrastructure related to quantum networks from an engineering perspective. Now, why quantum networks are so important with all the development that is happening towards an all-powerful quantum computer, our existing cryptography primitives based on mathematical complexities are becoming vulnerable to threats. And our data, our national security data, genomics data, medical, financial data, everything is at risk. Our communication infrastructure, if we look at, if it is at risk, then a lot of our security regimes will go for a toss. So quantum key distribution promises to provide a secure mean of communication based on the principle of quantum mechanics. If we look at the practical aspect of implementing a quantum communication network based on QKD, the two main challenges that we look at is the availability of ideal single photon sources and detectors, as well as the need to go large scale. Large-scale implementations of QKD are limited majorly by the high channel losses and the decoherence issues, but still a lot of effort has gone into large-scale implementation all across the world, as international and national level as well. The first QKD network was established by DARPA in 2003, and by 2004 it was further extended to multiple organizations, including Harvard University, Boston, Bolt, Newman, etc. This was followed by the European FP6 project, then followed by a QKD network in Tokyo, the Geneva area network, the China's hierarchical network, the Durban-based network, etc. But a major leap came in 2017 when China demonstrated a fiber-based QKD network, which was the longest at that time, with an approximate distance of 2,000 kilometers, which had a backbone network between Beijing and Shanghai, and 4 metropolitan networks at Beijing, Jinan, Hefei, and Shanghai with 10 nodes each. At national level also, we have made significant progress. Recently, 2 DRDO labs in Hyderabad demonstrated a fiber-based QKD network over 12 kilometers with a key rate of the order of kbps. A team at IIT Madras, SETS, and CDAC are working towards implementing India's first metropolitan area quantum access network, which is expected to be ready by 2023-24. When we look at the satellite-based QKD implementation, similar major implementations have been seen all across the world, with China in 2017 and 19 sending a pair of entangled photon using a quantum satellite, MISIUS, to 2 locations which were separated by 1,200 kilometers. Later on in 2019, China demonstrated world's longest space-to-ground quantum communication link, which was spread over 4,600 kilometers. Nationally, a team at RRI Bangalore, led by one of our distinguished speaker today, demonstrated free space QKD between two RRI buildings, which were 50 meters apart. More details on this will be discussed by Professor Urbasi Sinha today in her talk. And similar such implementation was further extended at ISRO's Space Application Center. So, looking at the implementations which are happening globally, it becomes very clear that it is high time that we at national level discuss the implementation possibilities, the difficulties that are associated with it, the challenges that we need to counter. And this webinar is providing that perfect platform to understand these things and take the discussion forward. With this, I would like to invite Dr. Paventhan, Director R&D at EarNet India, to share his thoughts and take the session forward. Sir, you are on.
Sir, you have to unmute. Dr. Paventhan, please unmute.
Sorry. Yeah. Good evening, everyone. So, on behalf of EarNet India, I express my sincere thanks to all the speakers who accepted the invite on a short notice. And also, I would like to extend my thanks to Executive Director SETS, Dr. Sharat Sir, and also ED Syrac Bangalore, Dr. Sudarshan, for extending all the support, organizational support in putting together this webinar event. And also, I would like to extend the warm welcome to all the dignitaries and delegates who have joined this event. So, as many of you might know, EarNet has carried out many national level projects in classical networking, both terrestrial and satellite networking. So, quantum is a new area to us. So, we intend to collaborate with scientists from Syrac, SETS, and also premier academic institutions, including industries in this new area. So I look forward to listening to the speakers and probably hand over for the introductory remarks to SETS CD and followed by Syrac AD. Yeah, thank you. Thank you, Doctor. Over to you.
Thank you, sir. Now I would like to request Dr. Sharat Chandra Babu, Executive Director SETS India, to please share his thoughts.
Good evening and welcome you all to this webinar, Quantum Networks, Realities and Opportunities. The title itself tells that there's a lot of talk that is happening on quantum networks, and probably everything is not real. There's something we need to understand what is real level of implementations that are happening and what are further opportunities, right? So it's very heartening to see the three key speakers of the day. Each one have excellent background. Professor Urbasi Sinha from Raman Research Institute, and Dr. Natarajan from SETS, Dr. Sonali Mahapatra representing the industry from Glasgow. So all of them have been working in the area of quantum networks in different directions, and also together, if we see, they are also part of implementation of some of the key networks. So it's I feel their talks would really bring out the realities and the opportunities and the practical aspects of the the quantum networks. So as we're all aware, I think we have been depending on the VLSI technology to speed of computing, speed of communication, everything. And we know that the feature size has come to a limitation where the quantum effect started may not be possible to move ahead. So as Feynman says, something has to be done, you do it by quantum, right? So the quantum computing has come because of we're not able to follow Moore's law by taking the semiconductor technology. The feature size couldn't come below probably 4 nanometers. There is a kind of a research happening at this point of time. So it's coming to an end, and what are all our dreams of Moore's law continues to happening from 1969 is not going to happen. So in this context, the obvious thing is to look for the quantum effects are stopping. So why not use the quantum mechanics to the computing? So that is the inspiration. Richard Feynman, Yuri Manin, all these people, Paul Van, these people have started in the 80s an analog quantum computer, and they are taking the advantage of superposition and quantum entanglement kind of things. Not only they, we later on people like Turing machine in the classical computing. We have the universal quantum Turing machine also defined by David Deutsch in 1985. So these are all important, landmark achievements in the area of quantum computing and quantum technologies to be used. So one of the things people started really surprised on the quantum effects is the Peter Shor's algorithm of solving the factorization, integer factorization problem in polynomial time. So that is really brought everyone started looking at, oh, this is quantum technology, not only gives the speed and probably we'll use it for the drug detection or very high-end intensive computing areas, but it will also affect our cybersecurity infrastructure, which is depending on the algorithms like RSA and ECC kind of algorithms, so which could be broken easily once the practical quantum computer exists. So that is one area of research happening, and in place of bits there are qubits, and people are talking about. I think Google has come out with 72 qubit system, and IBM is planning to have a 1000 qubit system by 2023, which appears to be reality because Google also in 2019 itself said that quantum supremacy can happen. So whether there was a debate on that, whether it's really achieved quantum supremacy. That is, quantum supremacy is the one where normal classical computers cannot solve in near future or even universal age. If the quantum computer is able to solve, we can call it as quantum supremacy, right? Quantum advantage, we can say, as long as any algorithm which is implemented by classical computer, if it is done at a higher speed, we can call it as a quantum advantage. So all these things debate is happening, and we have seen that promising technologies are coming. D-Wave has come with a very high-end system to solve specific type of problems and all that. So quantum computing is going, but still people are not sure when the practical, affordable quantum computers would come. But for the state actors, quantum computers building, the money will not be a problem. So when the quantum computer really comes, source algorithms or the Grover algorithm for the the conventional search algorithms, if the speed comes, if speed is going to be at quantum speed, at that exponential, double exponential speed, like Nevin's law they call, like Moore's law in quantum, they started telling that double exponential power is Nevin's law. Google's quantum head has come out with an equation like Moore's law. So if these kind of things happen, there is going to be a difficulty in terms of security, because so now we are focusing on quantum network seminar, and this is one area. I think quantum computers still not commercially viable, but quantum networks are already in place. Many industries world over are coming, and even in India, QNU Labs has set up and they have come out with some of the first versions. So there is a promise and there is a business case in quantum networks specifically used for key distribution. You know that sender and receiver, they need to share the same key, but till now the practices are very difficult, and by having a good computational power, probably you will be able to make. So in that context, the quantum-based key distribution, this quantum key distribution technique would be very handy, and it's probably secure. That is one of the key things. So existing systems, key distribution algorithms, classical algorithms are not probably secure. Once you have the suitable supercomputer, will be able to break. So this is the kind of a situation, and we know that now quantum and in other technologies are like quantum sensors and all that, and people are now talking about metropolitan quantum area networks. And as Vaibhav indicated, the IIT Madras, Syrac and SETS are working together on that, while they completed earlier some prototypes versions. And thanks to PSA office, which has funded way back almost 7-8 years back, funded IIT Madras to arrive at a fiber optic based QKD system. And later on, Ministry of Electronics started funding in the quantum area. A lot of brainstorms happened, and the PSA office, right from former PSA Dr. P. Chidambaram and present R. Chidambaram and present PSA Professor Vijay Raghavan, international experts also have come. Professor Vajnani kind of experts have come. So a lot of discussions happened, and Dr. Urosisin was also part of such meetings. Later on, MeitY also has started interacting and seeing what are the focus areas for the nation. So if you see the good ecosystem in terms of highest level is happening, and we can see that from these interactions we could see there's a lot of expertise in Indian academic institutes, in Indian R&D labs, and it's only thing is the time to come together. I think these kind of conferences will bring in people and their expertise, and people can connect to the thing. Like CDOT is working for telecommunication solutions, where they are also interested in quantum networks. And just now, Dr. Pavantan has told that ERNET is looking for the things. NIC is looking for this. So the need of the hour is to have a stable indigenous technology. And this is a kind of a multidisciplinary thing. Physics, maths, electronics, and computing, all kind of expertise is required in this. And I am very sure that this workshop will open some new vistas, new directions, collaborations in implementation of large-scale networks in our country. So with this, I would like to conclude, because I do not want to take the time away from the three expert speakers whose slots were already, I think, I just started entering into their slot. So I would like to stop here. I thank Dr. Pavantan who has moved this idea to conduct this during this week, and also Dr. Sudarshan for always saying yes to any technology effort, and to all our colleagues, and especially the speakers who have really chosen very right topics for the day to happen with their expertise and experience. I'm very sure that we all have very good learning time, and I wish you all a very happy learning time once again. Thank you all once again for patiently. Thank you.
Thank you very much, sir. Now I would like to request Dr. S.D. Sudarshan, Executive Director at Syrac, Bangalore, to share his thoughts. Thank you.
Yeah, namaste and good afternoon. So definitely, I should also formally thank first the great speakers. They're all esteemed, and we are also happy that we are having collaborations already with them, be it Dr. Gurubasi Sinha or be it Dr. Natarajan, and we have from industry side Dr. Sonali. So we have great speakers, that is for sure. Already I alluded, and the topic itself definitely talks of realities and opportunities. The key point here I would like to focus, since the other topics have been already highlighted by, I think Vaibhav gave a great introduction, followed by Dr. Pavantan and Dr. Sarath. The opportunity is something we need to size. When it comes in a big wave. Those who don't latch onto it, they lose out. So it is a time for us to create the critical mass, after which it will be self-sustaining. So from that perspective, a topic that talks about what is the ground reality, what is happening on ground, along with what it can bring, so that one can see the potential and what is available in the near future. That will motivate more and more people to change track and join the this quantum journey. So from that perspective, I think this is very important. And India, as we all know, have been a soft power and software power and IT power. That has been more or less undisputed. If you need to sustain, already as pointed from Moore's law and other things, can we sustain the supremacy in this computing era? For that, our entire manpower has to get onto this quantum technology, in whichever form it is going to bring opportunity for the country, and that will also make us, one of the economic superpowers by being part of the quantum supremacy efforts. So that makes such seminars very, very critical and very important. And today we can see, I know though the numbers was about 80 plus, some of them are there in the conference rooms, which I am already aware of. So we have more than 100 odd people joining, given that we have given less than a week time to organize this. From that perspective, this shows there is already a critical mass. And from CDAC Bangalore in particular, and CDAC in general, we are very happy that MIT and other organizations, GST and others have supported us along with Office of PSA. in taking the quantum research and development in a big way. And as we speak, we have a couple of projects with RRI, where Dr. Urvashi Sinha is the lead researcher in those projects. And we also are working with both IIT Chennai, IISc Bangalore, IIT Roorkee, DIIT from defense perspective. And then we are also collaborating with, of course, SETS, CERNET. They are all our sister organizations, or sibling organizations to be more appropriate. So we have been working with them. So it's a great journey that we are going through, but it is very important to re-emphasize and reconnect among ourselves, so that those who already taken the plunge into the quantum, they remain committed. At the same time, they bring in more and more people on board, and to ensure that without waiting for real quantum systems to be available, we also have planned for a very short quantum simulator demo in the end, so that at least a teaser and testing the waters is possible, even without really having a realistic quantum computer, which is anyway under development at IISc. We already have a realization at a very small number, since people spoke about 1000 qubits, so I don't want to mention the number at this point. But definitely there is a great effort going on, and India will be going forward. So it is time we all join hands together, and our collaborators have been excellent, and they are all renowned names and across the globe, not just they are India alone, but they are international experts. And we have had a discussion internally with Dr. Pavendan and Dr. Sarath, along with IIT Chennai, to continue this effort in upcoming days with other relevant topics. So this is not going to be a one-off seminar, but it is more or less going to become kind of a, if not a permanent series, at least a year-long kind of series that is going to happen. So you can look forward to more such events. And having the first one now, it's a great beginning. Going forward, we may be able to give maybe 2 to 3 weeks time upfront. That is what we plan to do. And definitely, I must once again thank all the organizers and our collaborators for joining hands, and Dr. Urvashi Sinha for suggesting her availability, because she is into several activities and her calendar is always kind of overlapping with multiple meetings, and she readily agreed. And that shows her willingness to not only share her experience, but to find a way to collaborate, rather than saying this time I'm busy, not available. She indicated alternate slots where it can be accommodated. So that is the kind of collaboration that we need in this busy schedule of new normal of COVID, where online times have been extremely overbooked. So definitely I must thank her, and she is working on multiple areas, including though the short resume talks of few things, they are also on to developing few quantum components also, which they are experimenting. So they have both hardware, communication, kind of software, quantum information theory, multiple expertise is there in RRI. And then from an industry perspective, Dr. Sonali, they are working on complete ecosystem from industry point of view. Syrac is working with an ecosystem from R&D point of view at this point. So that way it complements very nicely to hear the other side of the fence, so that what is the industrial based requirements, so that our development dovetails into their requirement, and there is a synergy across both the teams. And Dr. Natarajan is part of our collaborative team. So since they are hands-on, he can actually bring out what are the challenges we are currently facing. So it's a fascinating topic, and in the end, you will also given a, I will say, initial temptation or teaser by Henry, who will demonstrate the quantum simulator, and probably he will also mention about how you can get access in case you want to really wet your hands. So with that, thank you very much, and I'm looking forward to a very interesting session. Thank you, and back to Vaibhav.
Thank you very much, sir. With this, we'll move to our first session titled Long Distance Quantum Communication. Our speaker, Professor Urbasi Sinha. Hello.
Can you hear me?
Hello.
Hello, can you hear me?
We can hear you, madam.
Right. Yeah. So should I begin then?
Vaibhav, you want to introduce a little bit before madam starts? Maybe looks like Vaibhav dropped out.
Yes. So I think I'll just start sharing the screen and ensure that that is working. And,
am I audible,
yeah.
sir?
Yeah, now you're audible, Vaibhav.
Sorry, I think I'm still in the call, but I'm not audible.
Go ahead.
Yeah. So we'll move to our first session by Professor Urbasi Sinha. She's associated with the LAMP group at RRI Bangalore, that is the Light and Atomic Matter Physics group. She is also an affiliate member at the Institute for Quantum Computing, Waterloo, Canada, as well as the Center for Quantum Information and Quantum Computing at the University of Toronto. Her research interests include experimental quantum information and quantum computing, experimental quantum cryptography, quantum entanglement studies, quantum key distribution using satellites, single photon sources, entangled photon sources based on polarization, as well as novel degrees of freedom. I would request Professor Urbasi Sinha to please take forward the session. Thank you.
Thank you very much. Can you please confirm that you can hear me, because I hear lots of echo?
Yes, ma'am. Yes, ma'am.
Right. I will keep my video off for now because I want to save the bandwidth. RRI internet is playing up a bit today. So on that note, first of all, I would like to thank you, Weber, for introducing this. And of course, I would like to thank both Dr. Sudarshan and Dr. Pavinthan for being very accommodating and in fact even preponing this entire webinar to help fit my schedule. It's very kind of you to actually do that, and of course we have been discussing for a long time, and so we are also collaborating under this mighty project and so on. So thanks to Syrac, Sets and Ernet for coming up with this webinar and giving me an opportunity to speak here today. So over the next 45 minutes or so, I plan to talk about quantum communications in general, and of course long distance quantum communications in particular. And being the first talk in this webinar today, I will give some introduction, as I was informed that would be how I should pace my talk. So I'll give some introduction to the topic and then move on to the various activities that we are working on at RRI on this topic. So can you confirm once more that I am perfectly audible, and then I'll move to the rest of the presentation.
Yes,
thank you. Yeah, thank you. So, well, I think a lot of what I was going to say in the first few slides, has been nicely summarized in the previous, little speeches we heard from various people. But then, of course, there's no harm in repeating. And it is indeed true that today's science is tomorrow's technology. And the example that I have here is a rather gory one, and I'm sure you know what that is. But then having said that, quantum domain is in fact in that regime where a lot of synergy has to take place between science and technology. And so while some of us coming from a physics background, from an academic background, we tend to concentrate more on the scientific aspects of the problem, it is absolutely important and imperative that we have collaborations with engineers and people across academia, industry and various agencies, so that the science and technology go hand in hand, and whatever scientific outputs we do in our research institutes gets converted to technology in real time, and then that is how we see this progressing over the next few years. And of course, having said that, we are looking forward to the advent of this national mission on quantum technology and applications, which was announced last year, and I've been a part of the drafting committee for this, and so of course I'm told that it is in the final stages of approval, and so we are all very hopeful that this will start shortly, with notwithstanding Omicron. But then, this would be a very nice thing because it will lead to a plethora of activities and essentially a boom in what is happening in India today in terms of quantum technology and applications. As was mentioned, I belong to the Light and Matter Physics group, in short LAMP group, which is of course nice because I work with photons. And other than me, we have other faculty members who are working on other aspects of quantum technologies, whether it is the storage part with Andal, quantum interactions with Sadek, quantum mixtures with Shoktorishi, and nonlinear optics and ultrafast lasers with Reggie Philip. We, of course, work on quantum information, computing, and communications. For the next 5 minutes, I'll give a bird's eye view of, I'm sure there are lots of people in the audience who may not be familiar with our work or, maybe have not heard me speak before. So essentially a bird's eye view of our lab's activities, which are not quantum communication, before I move on and zone in on quantum communications aspects. And of course, this is literally a bird's eye view, and still we have these problems with social distancing and so on and so forth. So we don't have visitors per se yet, but then of course we are hoping that that would happen soon. And so this is how our lab looks on a good day when students are into photographing the things. Otherwise, we have lots of screwdrivers and stuff hanging around, which are not making their presence felt much. But then this is how a quantum optics lab is expected to look on a given day. And we have a clean room, so we have all these air curtain and air shower and so on. Now, for the people here who may be not from this given domain, the main workhorse of what we do, of course, happens to be working with single and entangled photons. And so if you really wanted to know more about how to make these photons, I would suggest a review that I wrote with my students. I think I humbly think that it's quite nice, and so please do have a look, because it's not just one or the other. There are several alternative approaches towards actually manufacturing photons, and it's of course much easier said than done, given that it's not just about dimming down the light in my room and calling it a photon source. You have to actually satisfy certain properties of the statistics of the sources, and that is what makes it technically and technologically interesting. And there are different types of sources and so on. So what we are primarily working on right now is based on nonlinear optics, and it's called spontaneous parametric down conversion. And I won't get into the details here, but then these are pictures from the lab which tell you and show you regions where we have entanglement. So if you can see my little arrow here, which may be moving on your yellow dot, that is where the intersection point happens, and that is where we define entanglement. Okay, and going on to the various types of work which we are doing other than quantum communications, of course, one of our primary interests and activities today is and always will remain fundamental and precision tests of various quantum optics and quantum mechanical phenomena. Because of course, that is where a lot of our interest lies, in understanding the basis of all this better. Because of course, if we do that, then tomorrow, this precision bound that we can put on various principles will have a natural role to play in the precision of the technologies that they're applied to. So this is a series of work that we have done in theory and experiment on the bound on the superposition principle in quantum mechanics, and we have found a correction term and measured it for the first time globally. Here we have what is called the Hong-O-Mandel dip. Again, for people who know this, you know that this is a characteristic of photon sources. And if you have perfectly indistinguishable single photons, you're going to get 100% dip. This is what we learn in our quantum optics textbooks. We challenged that, and we said that we can actually do this using classical pulses. So you can see, well, of course, it comes from a fundamental perspective, a very important result, but it also questions the technology that was being used so far to characterize photons. And so Hong-O-Mandel is not the ultimate characterization. We need to do the complementarity test. So this is how, science and technology are, I would say, have undergone a very peaceful marriage in our lab, and they are peacefully coexisting so far. Okay, and this is an example of something which, I'm sure is a lot of interest to industry, because of course, while this happens to be a fundamental quantum result, which was, published last year in Physical Review Letters, this is actually a new technique for quantum state estimation. Of course, for people who are working on this, that, whatever you want to do, whether it's a network or whether it's a quantum computer, ultimately everything boils down to how well you know the quantum state. And so all the applications that come after that, right? So this knowledge of the quantum state is very important. But then, of course, if you measure a quantum state, then you disturb it, and then, that's it, right? So you can't just do direct measurement of a quantum state, unlike, let's say your body temperature, which you can just measure with a thermometer. It's always indirect. And the traditional method is similar to the CT scan, where you take different projections and then do a reconstruction. That is called tomography. What we have done is proposed a new method using interference, which is called interferography, where you can do this with a single shot measurement, as opposed to the d² number of measurements that are required in tomography. So this is a fantastic scaling advantage. And while our experiment serves as a proof of principle, we have also shown how this can be miniaturized into a tiny box of, a centimeter size or something, and essentially told you how to make a little device which you can carry in your pockets and estimate quantum states as you speak. And that is something which we are hopeful will be done by a suitable industry, because we are not necessarily the right people to actually manufacture these things at RRI. So just to give you an example of the theme today, which is really about how physics and engineering and science and technology can go hand in hand, right? Of course, in quantum computing and QKD, we are working on what is called higher dimensional quantum computing. And that is something which, in fact, we were told about qubits and so on earlier. But then if you don't use qubits, if you use higher dimensions, we have what are called QDITs. And that is what we are focusing our attention to in our lab. Towards quantum computing. And again, a popular level invited article is something that you can have a look at, which was in the Scientific American last year. And of course, I might say that if you try to click the link, you might be, led to a paywall. And of course, I'm sure the people I'm talking to, Syrac sets, they can afford to pay. But then if you really wanted to not pay, then just drop me an email and I can send you a PDF copy informally. Okay, so if you're interested in reading more about this stuff. Quantum measurements is something we are very much into, and doing this better and doing this more precisely, coming up with new tools as we speak. Studies of entanglement, manipulating it to make it live with us for longer. For instance, we talked about quantum computing. Suppose we have an algorithm which requires entanglement for that protocol, then we want that entanglement to stay while we are doing the gate operations. And there's always this tussle between how fast decoherence will act and how fast your gates will be applied. And so we have come up with a way where we can actually hold on to this entanglement for longer and essentially prevent it from dying or decaying to zero by interacting with the environment. And so this is an experiment which also is now near completion. Now going on to the topic of today's discussion, which is of course quantum communication, and in that, as we know, the main quantum feature is quantum key distribution. And as I say, and I'm sure all of us agree, this is the most quote-unquote practical quantum technology. Why is it practical? Because of course this is something which is already in product form. Both in India and abroad. So then, in terms of TRL, this is much higher than, let's say, the quantum computers, which are at a lower TRL level. But having said that, why is it important? Let's go on to that. So why you should worry? I mean, of course, worry is a word, but then why should we care about this field at all? Now, why should we care about the field if we are actually guilty of any of these four applications that I have listed here, whether it's a credit card purchase, whether it's online banking, voting, or defense, strategic communication. And I know I'm talking to an audience which is doing even all four of them, many of them, right? So these are all examples of strategic communication where, security is of prime concern and prime importance. So you don't want your information to reach a third party that is not the intended recipient. And so till now we have been working with classical cryptography to keep information secure, but these will be compromised with quantum computers, and that's why the solution is quantum cryptography. And of course, what is wrong with classical cryptography is that unconditional security is not possible. For instance, the RSA protocol is based on the mathematical complexity of factoring large numbers. But as we know, Peter Shor here on the right, he came up with Shor's algorithm, and that algorithm, when it runs on a quantum computer, is going to change the mathematical complexity of the factorization problem and make it easier, which means that RSA protocol is not going to remain secure anymore. Okay, so computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack. New algorithms could be developed for classical computers as well, and of course, Syrac is our country's supercomputing, has all the supercomputing expertise. So I mean, they could come up with some algorithms for classical computers as well, which could beat the factorization problem. It is not there is no proof, there is no theory which tells you that factorization is unbreakable, and so it is a matter of time or clever ingenuity when this could happen. Realization of quantum computers seems to be becoming more and more a reality. So mine security should be independent of future advancements in computational power, new algorithms or new technology. That is, it should be future secure. And so this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem. And that is where quantum key distribution plays the key role, literally, because that is the quantum aspect of this. And of course, when we talk about networks, there are many layers which are before and beyond the quantum aspects. And of course, all this needs to be integrated so that we can have the quantum network. And so what we are focusing on here right now is the key distribution layer of the problem, right? Having said that, one thing I always like to say, this Krista from Microsoft Research, she actually made this famous statement that the RSA 2048 challenge problem would take 1 billion years with a classical computer. A quantum computer could do it in 100 seconds. But then having said that, please remember that there is a rider here, that a quantum computer which would actually be able to do this would require 4,000 qubits and 100 million gates. Okay? And so it is, of course, safe to say that we are not there yet. But then does that mean that we become complacent? And of course, the answer to that is no, because this would happen sooner than we think, because quantum computing research is going at super exponential speed. So then we need to ensure that all our bells and whistles are in place over the next few years so that we would have replaced the way of doing things with our quantum counterpart, so that the quantum computer is used for its beneficial purposes and not for this purpose, which is clearly not beneficial. And so it's not a threat anymore, right? And so we need to act now and get our acts together so that this can be mitigated. As we know, this is happening. So how does quantum mechanics protect information? That is a talk by itself, and of course, not necessarily something I want to get into today, but then there are several principles of quantum mechanics which are used for protection of security in QKD, whether it's uncertainty principle, no cloning theorem, or quantum entanglement, for instance. So these are the key ones which are used in the most well-known quantum protocols, and so there are different approaches to quantum key distribution. You can have prepare and measure-based QKD, where the security is based on the uncertainty principle. And so popular ones are the BB84 protocol, which was the first QKD protocol. And in fact, as you may know, it has a Bangalore connection because this was first announced in a conference at IISc in 1984. So it was first conference proceeding from India. And so we have a QKD connection which perhaps we should remind ourselves of, and so we want to use that and bring about a more modern connection where we can go towards doing novel things in QKD which are globally competitive. And then we have the B92, which is a variant of the BB84, which, as you can see in the naming of QKD protocols, we very much go by years in which they were proposed. So BB84, B92 happened in these years. Similarly, we have entanglement-based protocols where the security is based on entanglement. We have the BBM92, but before that we had the Eckert 91 protocol, which was proposed by Arthur Eckert. In fact, he gave a very nice colloquium at RRI a few days back, and it is on our YouTube channel. So if you are interested in this topic, I think it would be very nice for you to hear the colloquium by someone who actually invented entanglement-based quantum cryptography and has explained it really nicely. So having said that, when we go to the BB84 protocol, the general idea is that, we are talking about 4 different basis choices. So we have the most important part of this protocol is, of course, the single photon source, because, without the single photon, we would have all sorts of attacks and vulnerabilities creeping in. So the single photon source is something which needs to be very reliable. And then I'll just use an example to give you a flavor of how this protocol works. So these are my color encodings. So for rectilinear, I'm doing R0 with red, diagonal 0 with yellow, and then again rectilinear 1 with blue and diagonal 1 with green, and so on. And so this single photon, when it comes out, it is encoded randomly in one of these 4 possible choices, okay, of polarization, right? And so this random number is again a very important factor in a single photon based protocol, because, you know, without that there would be vulnerabilities again. And so once that is done, it gets some encoding, it makes its way to the Bob site, where again Bob does a random selection of bases to do the measurement. So once that happens, we have a set of bits on each side, and this is just an example that I'm chalking out here. As you can see, for some of them, the bit values would match, and for some of them it wouldn't. So what Bob and Alice would do is that they would share their basis information on a classical channel. Mind you, they won't share, of course, the bit value, because then it could be accessed by anyone. So they share the basis information, and then they only retain those bit values which correspond to the cases where there is a basis match. And these are the ones that come out in my random example. So this is the idea: prepare, do a random selection of bases, random selection of polarization between the two orthogonal bases, and then send the stream of photons to Bob. Bob does a random selection of bases and measures in each basis, and they record these things for the detected photons. And together they send the timestamping and basis selection over the classical channel, compare it for correlated events, and consider only those events where basis choice match, and discard the rest. And so these are the critical elements then to be developed in Qkd. As I said, the quantum source plays a very important role, because if there are vulnerabilities here, that will pull its way through the entire protocol. There are a certain amount of simulations that are required in order to ensure that the protocol is being done correctly before it is actually implemented. And then there are classical post-processing steps that need to be done, like privacy amplification, error correction, and secure key, to get the final secure key. And so, as you can see, even in this series of steps, there are, of course, main quantum elements, but then in the end, we do have classical post-processing, which we share with classical cryptography, right? So these are common elements in Qkd. But then the main focus is, of course, the source and the protocol, which are based on quantum physics, yes? Coming on to entanglement, while of course, BB84 and protocols like that work fine without entanglement, if we want to go towards device-independent quantum key distribution, and in fact, this is where you should listen to Professor Eckert's colloquium, because that was all about this slide, really. Why do we need entanglement-based Qkd? This is the general idea, and of course, a lot of work is going on towards that. So far as experiments at RRI are concerned towards this topic, well, we have, of course, performed all the standard Qkd protocols over the last several years using our single photon sources based on SPDC and using uncertainty principle for the security. This was our BB84 experiment, and then we went on to a novel version of the B92. So B92, of course, was established in proposed in 92, but then, what has been a focus area for Qkd over the last several years has been, improving upon the existing protocols so that we aim towards higher security and higher key rate, because ultimately, if our aim is long distance quantum communications, then we cannot afford to live with a low key rate. We want to increase it so that we can mitigate the distance based losses. And so what we went on to do is come up with novel implementation based on this one proposed in 92, where we ended up with competitive key rate and quantum bit error rate. Okay, and I will skip the details. You can have a look at our publication for that. But then having said that, B92 is a variant of the BB84, as I said, and except that it uses only 2 basis choices. And this publication here is something that you can have a look at to have details about our protocol. But it looks like this. And this is the Alice and Bob setup in total. This is the Alice part and this is the Bob's part. And this was done within the lab over 2 meter distance. And this is the schematic of various optical components and so on. But then the important thing here is, of course, the key rate and the QBA. We have a key rate of around 50 kilobits per second and a QBA which is restricted to 4.8%. And for people in the know, you would know that 4.8 is the information theoretic security threshold for the B92 protocol. So essentially, this means that from information theory calculations, we know that the quantum bit error rate of an experimental implementation of B92 has to have a QBA of maximum 4.8%, because if it goes beyond that, then it's not a good candidate for actually giving rise to a secure key later. Okay, and so we went into a lot of optimization algorithms and techniques to restrict this to being, actually useful for security. Although ours was, of course, a proof of principle demonstration, but having said that, it is aimed towards a project which aims to do secure communication, and so this was very important to restrict it to that. And in fact, to our knowledge till date, the best available B92 setup using SPDC source has reported a key rate of 31.6 kilobits per second and a Q bar of 10.5% for a 0.4 meter transmission. So as you can see, our demonstration has a higher key rate, lower Q bar and longer distance than the existing record so far. So we're very happy with that because, of course, not only is it an important demonstration, but also it is important from a global perspective. And why B92? Well, as I said, there are novelties that we introduced in the setup. So we have used heralded single photon from the SPDC process. Mostly the demonstrations are using weak coherent pulses. We have used a true random number generator from, what's called a quantum random number generator. We have done some interesting techniques of correlating polarization with the temporal degree of freedom to get the security, up by reducing the noise, and then a high rate and key rate and a low Q bar as well. Right. And of course, we are very happy with this experiment because indeed this is our country's first published experiment in free space quantum key distribution. Mind you, this is free space, and of course it is an internationally peer-reviewed publication. So that is important for our project, but also overall, right? And of course, students would do this. So they use the key and encrypted popular image. But then importantly, the encrypted image looks like this. So you can see that it worked very well, our key. And this was the decryption. And this is my students' thing, that if it did not work, we would end up with a different image from what we would have anticipated. But having said that, we then went on to entanglement-based Qkd protocols, which we performed with our dedicated polarization entangled photon sources, and using entanglement measures as the source of security. This is a schematic of the source, and this is the complete setup. Okay, and we achieved a very high concurrence. Concurrence is the measure of entanglement, so the highest value would be 1, and we went up to even 0.995. And so you can, the amount of concurrence plays an important role in restricting the Q bar. So if you have, an entanglement of 70% or 60%, that is not going to be a very useful for your, Qkd protocol. So it took a lot of time and energy to actually get these numbers to be competitive. And this was the paper that I mentioned earlier, so do have a look. We also have a patent application now on this paper. So people don't just get the message, they keep calling even when I cut the calls. So sorry about that. Having said that, this is something you can have a look at. Okay, and this is actually something which gained a lot of, appreciation, our work in terms of, its importance. And because the work was not only about the first experiment, but also we went on to develop a simulation toolkit for Qkd. And this was, I would say, serendipity, actually, because people in research, they always state things exactly the way it happens. So we wouldn't say that, this was our life's intention to create this toolkit and software. We just happened to, when we started off several years ago in RRI, the idea was that we wanted to see, find a simulation kit online and see how our Qkd protocol would work before actually investing resources, which are always scarce. And so we found that, these are all available. But having said that, none of these actually does a combination of the things that we want, which is a quick and precise simulation of physical processes, considering realistic imperfections, simulation of single photon source, detection module, and background noise in more detail, and generalization and applicability to all existing protocols. And so the idea is that, with Qkd becoming more commercially viable, and of course today's audience is the right one to appreciate that, advanced engineering techniques are being proposed. So direct testing of these techniques in an optical setup is not very cost effective. And we know that, whatever it is, it's always difficult to get funding for something unless you have some proof of principle hanging somewhere that this. By enabling simulation of Qkd protocols, considering physical process models, realistic imperfection, and experimental non-idealities. And that's very important because, as we know, Qkd is not it is actually an experiment. It is not just theory. So experiments come with errors and non-idealities, and of course the softwares that currently exist, they seem to be developed by software developers, of course, and you know, they don't pay that much attention to these practicalities. So we have tested its prototype's performance with an in-lab free space implementation of the B92 protocol, which is what is the publication also has. And we followed what is called the Agifall model of software development, which is a combination of agile and waterfall model. Okay, and so this is something which basically is a top-down approach, where it's a hybrid between waterfall and agile. So the waterfall model is the top-down approach, and the agile provides it with an iterative approach. So there are these modules and sub-modules, and so the idea being that if we come up with a better version of a sub-module for any physical process or imperfection, we just replace that rather than write the whole thing top-down. So this is the best of both worlds logic, and that is how our software development happened. Okay, and we also went into a lot of optimization techniques to increase our Q rate and Q bar, which I'll skip for now, but it suffices to say that, you know, this is, we had these different strategies where we optimized on symmetry versus asymmetry and so on and so forth. And the comparison is very nice between simulation and experiment. As you can see, you know, this being, the experiment, and this is the simulation. And now we already have a new version of this, which is currently under the patenting process, which has even taken care of further non-idealities compared to this published version here. The snapshot of the algorithms. Okay, now going on to, of course, long-distance quantum communications. So, you know, long-distance quantum communications is something one can do once one has done this at a lab scale. So this is something which, of course, I have spent a lot of time and energy convincing various people, who are, of course, in decision-making domain, that, you know, we have to have some time as a country for some capacity building before we can say that, you know, we are going to have larger aims, because without learning the alphabet, it's very difficult to write a novel. And so then, having said that, of course, the novel is what we are all interested in, and we, at least at RRI, we have definitely written some chapters of it. And so why do we need, what is the big deal about long distance quantum communications? So here, let us revisit the distance limits for quantum channels. So when you have ground-based quantum communication, it's typically, up to 100 kilometers, demonstrations to a maximum of 300 kilometers have happened. But then beyond that, the line of sight is a problem, because in ground-based communication, the sender and receiver need line of sight. And so beyond that, the Earth's horizon comes into the picture. So you can't keep on having line of sight for longer than a certain distance. Of course, we would think that we would use fibers as a solution. Optical amplifiers to amplify like we do in the classical networks. So because of course we would violate no cloning theorem. So we need to come up with some out of the box solutions here. And these are the possible solutions. One of them was discussed earlier today, which is on the trusted repeater based approach. And this is a slightly older slide. Now we have the 2000 kilometer one between Beijing and Shanghai. Then we have the, quantum memory and quantum repeater approach, which is actually an entanglement-based approach. And then we have satellite-based quantum communication approach. So the second one is something we are actually pursuing at RRI under the DST's Quantum Enabled Science and Technology program. And just a general idea of how a relay works is, so we have an entangled source, we have another entangled source, and of course, 1 and 2 are entangled, and so are 3 and 4. But what we do is we make 2 and 3 undergo what is called a Bell state measurement, as a result of which 1 and 4 get entangled. And so this way we can actually, swap the entanglement in some sense, and it is basically now between 1 and 4, and we have increased the distance. So this is what is called swapping, and this can be extended to long distance along with memory. Okay. Now, what about satellites for long-distance QKD? Satellite bridges the large gap between ground-based quantum networks. And so this is the general idea. You can have a satellite which has, let's say, I'm talking about entanglement-based QKD. Of course, you can do single photon-based as well. So this is an entangled photon source, and then you can have a photon sent to one ground station and another photon sent to a different ground station, and you can establish a link. The other idea would be to have 2 ground stations. Both of them have photon sources, and one photon is sent to the satellite when it passes over this ground station. And when it comes here, this guy sends its photon, while the pair photons remain on ground, and that helps in establishing a link. This is what is the difference between what is called a downlink versus uplink QKD. While downlink QKD has been demonstrated by the Chinese group through the Michia satellite, uplink QKD has not yet been demonstrated globally. And in fact, our project at RRI has an ambitious aim of hoping to make this a reality. Okay, and so this is a snapshot of where we could perhaps reach with direct ground-based links and satellite links and repeaters. Ultimate idea being that a combination of all of this is going to give us the global distances between 5,000 and 20,000 kilometers. And this is what, of course, is the global quantum communication network. And so we are working on this aspect right now, where we have the satellite-based quantum communication linking to ground stations, which are, of course, at a long distance apart. And this ground station, on the other hand, can then, even be connected to a fiber optic network, which then connects to various service providers, right? So essentially, a combination of fiber and free space is going to give rise to this global network. And of course, at the moment, we concentrate on the local network, which is the countrywide, and then we go a step further, and hopefully in most of our lifetimes, we actually see that happen as well, right? And there are, of course, different approaches being considered by different countries. Satellite QKD, of course, the Chinese have a lead there with already a satellite out there. That is the only quantum satellite right now. Then we have other countries working on different approaches towards fiber and free space QKD. These are essentially the current records for various studies. Okay. Our experiment is called Quantum Experiments with Satellite Technology, or QUEST, which is a collaboration between RRI and ISRO. And this started in 2017. This is India's first project on satellite-based QKD. And in fact, it is amazingly close to the Michia satellite launch, because before that I had spent around 4 or 5 years trying to convince various people that this is something we should do, but then it was treated more a little bit like, I would say, science fiction. And so on and so forth. But then one launch of a satellite, successful launch, actually did very quickly turn the fiction to fact, and we got our project funded. And so that is how we started off in 2017. And the project overview is, of course, establishment of information theoretically secure communication, quantum communication over large distances, using a satellite as a trusted node between 2 ground stations in India. Okay, and we are working, of course, we have done both single photon and entanglement-based QKD, but our aim would be to actually establish entanglement-based QKD through this project. And these are our ground stations at RRI. And so you can see, in fact, this is, what we demonstrated towards the beginning of this year. This is our telescope station, and what we demonstrated is quantum key distribution between our lab here and another lab there, over a distance of 50 meters. And the 50 meters was essentially because this is the only free space link that is available in our institute, which is not, in the path of a tree. So, RRI is a very, very green-friendly place. I'm sure some of you have been here. You can already see some of the trees here. But miraculously, this particular link does not have a tree directly in its path. Otherwise, we would end up with, we would not cut trees and so on and so forth. So this is the only free space link available, which is clear. And so that is how we ended up doing this demonstration of entanglement-based free space quantum key distribution between 2 buildings using an atmospheric channel. Again, as was mentioned, this was India's first such demonstration. And we achieved, at that point, we achieved, not a very high key rate or QBA, but then they were good. And now we are improving them. Because, of course, after that, we went into lockdown, and then we came back, and we have now improved upon them, and those will be available shortly. And, of course, we are very honored that this work received a lot of appreciation as well. And, of course, and it's very important that, this sort of set the basis to go towards longer distances, because once we beat the atmosphere over a shorter distance, then we go longer distance and finally use a satellite. So this is basically a stepping stone towards the ultimate aim of satellite-based QKD, and that was very nice. And of course, this is how we did the work, in the kind of last year when this experiment was happening, and we still continue in this current mode of masked experiments. And however, hopefully, our enthusiasm remains intact. And very glad that our quantum key distribution experiment was actually recognized by the Department of Science and Technology as one of its 20 major success stories in 2020, along with our quantum state interferography experiment for quantum state estimation. And in fact, the Vigyan Prasar, which has this channel called India Science, which I would encourage people to have a look at, because it's a very nice OTP, it's a channel, online channel for Indian science, news and so on. And so they recognized us as one of the top 10 science works of 2020 as well. And regarding quantum communications, while I have spent more time on discussing our journey from various demonstrations within the lab to outside the lab towards satellite-based QKD, we are also working on different other aspects of quantum communications, whether it is integrated photonics-based QKD, which is an Indo-Italian collaboration, quantum teleportation, and relays and repeaters, which is under this DST project, as I mentioned. And of course, we have the Center for Excellence for Quantum Technologies from MIT, and where we have the collaborations with IISc and Syrac, where we are working on, again, fiber-based teleportation, as well as device-independent random number generation. So I also happen to be a member of the focus group on quantum information technologies for networks from the United Nations. And this is a very nice group, which is actually working towards developing standards for quantum technologies. As we speak, there is more and more interest in this. But, when I say I have demonstrated BB84, and if someone else says, we should at some point mean the same thing. You and I cannot have different expectations from the protocol. So we should have some minimum ISI mark, for quantum technologies as well. And so that is what we have been evolving through this focus group, which meets regularly. First, 1 or 2 were physical meetings, and now, of course, it's all online. And in fact, that is a meeting that is also happening tomorrow evening, and so on and so forth. So this is a very interesting domain. I think our country should play a more important role and start playing more, taking part in this standardization developments as well. And so here, of course, we see these various records which have been achieved for quantum key distribution. This was from Chinese group, intercontinental quantum key distribution. These are the quantum network test beds in Russia. And these are various groups working on various aspects. This is their field test of industrial QKD systems. This is their satellite QKD roadmap. This was this Beijing-Shanghai link, which was already talked about. And this is a very interesting slide, which was work done by this dedicated team in this company to figure out what is the market share for QKD systems as we move along. And so you can see we go up to 2028, and you can see the growth is clearly exponential. And so we expect that it would be close to $8,000 million by 2028. And the sectors that would play a role would not only be the military, but also civil government and, others. So it will be shared by different sectors. And so we see a lot of usage for QKD across various sectors and through dedicated study that was done. So, well, this was during happier times when we actually had physical conferences. This is January 2020, and this is in fact Jianwei Pan, who is leading the MISSIUS mission in China, who visited us last year. And so, of course, we hope we go back to these times soon. With that, I think I'm pretty much on time, and I would like to thank you for your attention. And I hope there were people who were listening all this time, and I wasn't cut off. Okay, now is the moment of truth. Okay, somebody has to speak to reassure me that, okay, fine, great, yeah.
Thank you very much, ma'am.
You're most welcome.
It was really very descriptive in terms of the work that is happening at RRI in your group. So there are no message boxes here. I would request people to please raise their hands. We will unmute you if you have questions. So I think If you have any queries, I request you to please raise your hand. You can unmute you and then. Okay. Thank you very much, ma'am.
So Urvashi, I just wanted to ask a simple question on the free space experiment that you carried out. What is the frequency in which it operates?
So it is, we always talk in terms of wavelengths. So it is 810 nanometer.
Oh, I see. Okay.
Yeah.
That's a kind of precursor to the satellite link.
Yes. So 810 nanometer is actually a very nice wavelength because it has a nice window. So for satellite QKD, of course, we need to ensure that, we are actually sending photons in a wavelength where there is a clear window, in the transmittivity versus wavelength, that not all wavelengths are equally going to reach different levels of atmosphere. So 810 is a good window.
Oh,
yeah.
That's interesting.
Thank you very much, ma'am.
Thank you. Yeah.
In the limited time, you have covered so many things for us, introduced us to so many things. We could pick up from where we can get started in this particular domain, starting from NMQTA to the quantum sources, interferography, the Qdits implementation, the Qkd basics, PB84, B92, the entanglement-based implementations at RRI, quantum relays, quantum memories, satellite-based Qkd, etc. The Quest program that RRI is involved in. Thank you very much, ma'am. So with this,
Thank
we
you
will
very much.
move on. With this, we will move on to the next session today, that is building a quantum technology ecosystem of the future and industry perspective. And for that, we have Dr. Sonali Mohapatra, who is the space applications lead at the Space Engineering Practices Craft Prospect based in Glasgow. She has research interest in quantum gravity, gravitational waves, black holes, stars, optics, AI, and quantum information. And she works towards conceptualizing and realizing novel applications of quantum technologies in space. I would request Dr. Sonali Mohapatra to please take the session forward.
Thank you very much, Natarajan. I think there is a hand up in the audience. Did we want to take that question?
I think that is addressed, ma'am. So I guess you can go ahead.
Are you able to see my screen then?
Yes, ma'am. You can see it.
Okay. Thanks very much, and thanks very much to Dr. Sinha as well for the previous really good talk. It covered quite a lot of it, and I managed to jump in the middle of that. So basically what I'm here to do is kind of give a complimentary talk of the industry perspective, a little bit about myself. I am space applications lead at Craft Prospect, which is a company, which is a small satellite company in Glasgow in Scotland in the UK. I myself am from India. I actually did my bachelor's and master's in IISER Kolkata, so Indian Institute of Science Education Research Kolkata, and then continued to do my master's and PhD at Perimeter Institute and University of Sussex. And within all of that time, worked on quite a few different projects and theses which kind of spanned between optics, AI, quantum gravity, fundamentals of quantum mechanics, few things about quantum technologies, and so on. So after I graduated with my degree in particle physics, I then kind of decided to bring my quantum expertise into the space sector. And that's where I found myself doing a postdoc, jointly a postdoc between the University of Strathclyde within their quantum technologies group, and then acting as a knowledge transfer partner to the engineering domain in Craft Prospect, which is a company which was exploiting some of that IP into building of the actual engineering hardware and commercializing a lot of these technologies. I then went on to kind of lead the quantum team at Craft. We set up one of the first test benches in the country, which demonstrated quantum key distribution on a lab and a test bench. And then we basically got our own mission, which is the satellite QKD mission, to demonstrate satellite quantum key distribution from orbit around the Earth. And we are currently basically in the very, very final stages of building everything for that mission, testing for the mission. So in my talk, I'll be talking a little bit about what I did or how I facilitate building a quantum tech ecosystem of the future from a space industry perspective. So I think I'm just going to very quickly go over some of my slides because I think a lot of these fundamentals have been covered by Dr. Urvashi already. So as all of us are aware, we are living in a very, very data-centric world. Especially during COVID, we have a lot of us have shifted to remote working. A lot more data is being transferred online. Lots more billions and billions of pounds and dollars and rupees are all being spent online in transactions every single minute. And so encryption becomes more and more and more important because the amount of data we, I think, produce in a day or in a minute, can't remember that quite exactly, but it's around 480 exabytes of data, which is a humongous number. And so a lot of the encryption mechanisms today rely on public key encryption, which is something that uses symmetric encryption, and it bases itself on mathematical complexity. So when I say it bases itself on mathematical complexity, what we mean is, for example, you can take two really big prime numbers and you get a computer to multiply those really big prime numbers. And at the end of it, you get a really big number again. But when you ask a normal computer to find the factors of that huge number at the end, you can calculate that for a normal computer, it will take more than the lifetime of the universe to crack that kind of encryption. However, things have changed. Quantum computers are on the horizon. Well, not just on the horizon anymore, because we already have real quantum computers. They're just very, very big at the moment, and they're not large scale in the sense that we only have a certain number of qubits, which are not enough to break our current encryption methods. However, that is very, very evolving very, very fast and almost exponentially. And the predictions by FactBis Insight and a few more other, review papers as well as review white papers is that by 2027, we will be having around, hopefully the 4,000 to 5,000 stable qubits to build large-scale commercial quantum computers. And my expertise is not exactly on quantum computers, so I can't tell you, what other roadblocks there, what other obstacles there. I'm sure there are many, but what I can tell you is that while there are many good things that will come out of quantum computers being large scale and commercial, we also have to protect against this threat against our encryption, because all of our phones, all of our OTPs that we get on the phones to go into our bank details, our finances, our hospital records, government records, all of them are stored. And while many people do not do it very well, we still have quite robust encryption, and we want to go forward making sure that cybercrime syndicates don't end up getting all of our money and all of our data. So governments around the world and researchers around the world have led the way to two different kinds of quantum-resistant cryptography, post-quantum cryptography. And then they are very actively being looked into by governments as well as companies around the world, as well as universities. One of them is quantum-resistant algorithms like PQC, post-quantum cryptography, which is basically it integrates more easily into existing IT infrastructure. It is kind of also based on algorithms again. So it's not proven to be perfectly secure against all kinds of attacks in the future. And if, let's say, we find better quantum discoveries and advancements in the future, then we would be able to break those quantum resistant algorithms because they are, again, based on the numerical methods and algorithmic methods. However, we also have quantum cryptography, which is quite an early stage technology, but QKD, quantum key distribution in particular, kind of provides us with future-proof encryption because it relies itself on sending information encoded in the quantum states of a particle like a photon, which is a single light particle. And anybody who's trying to eavesdrop on this particular quantum state would alter that quantum state and will leave some trace in the transmission that we're doing. So basically, I mean, all of you listen to Dr. Bashif about what is quantum key distribution. This is just a snapshot, and I like using these colors because this is just my company colors. And so this is Alice having the company headband because we are making the satellites. And then you have Bob, which is a ground station. And the ground station we are building is in collaboration with the University of Bristol. And that is a mobile ground station, which can be taken on the back of a van and transported to many different sites as necessary. To get around the problems of having cloud cover on top, for example. And I've just given it a Scotland tartan colors over there because it's going to be in Scotland. So basically what a satellite is going to be doing, quantum key distribution needs a receiver and a transmitter and a receiver. Alice has the transmitter, transmits photons. It can, so there are multiple different kinds of quantum key distribution, as again Dr. Ulbershi was saying. There's entangled photons QKD and there's single photon QKD. And in my talk, I'm going to be focusing on single photon quantum key distribution because that's what we do at the moment. So in a single photon quantum key distribution, let's pretend that right now we are not going to satellite QKD and we are just doing terrestrial quantum key distribution. In the very basic sense, what it means is that Alice's transmitter, or I will have a transmitter, let's say, and I will be transmitting single quantum particles, single photons over to the receiver. The receiver will then measure those photons and find out what information I have encoded in the photons. For us, we encode the information in the polarization state of the photons, and that is transmitted over what we call a quantum channel because this is just quantum transmission. You would also need another public channel, authenticated classical channel, over which you can do the post-processing after Bob has received all of those information of the key. Bob then does all of the post-processing in collaboration with Alice, and then by the end of all of that huge process, you have a key which is distilled from a raw key that was sent by Alice using those photons that you can use to perform future encrypted communications. So quantum key distribution is just a method of exchanging that key, distributing the key. The key can then be used by service providers to offer you security, to offer you a method of doing secure communication with your banks, for example, or anything like that. So there's quite a few different terrestrial quantum key distribution companies around in the world already. It has been highly commercialized already. There's ID Quantique here. You can see the box they have, and Toshiba also have the world #1 in terms of how good quantum key distribution, terrestrial quantum key distribution systems are being sold in the world at the moment. So, and there have also been a few quantum key distribution networks that have already been laid out around the world. So obviously China with the MyScience mission, it showcased satellite QKD, and it also has a terrestrial quantum key distribution network as well as a satellite quantum key distribution network laid out already, which it uses. Cambridge area in the UK already has a quantum key distribution network that is in active use. Again, in the Netherlands, there is another network of quantum key distribution that is in active use. And I know that there's plans for another quantum key distribution network. All of these are terrestrial to be put in London as well in the next year. So the problem with terrestrial QKD is that there is a distance limitation. You can only send photons through either fibers or through the atmosphere up till 500, 600 kilometers. And while there is active research on whether we can use quantum repeaters or not, because that'd be great if we have quantum repeaters, they are not yet practically demonstrated. And so that is not a feasible solution to go ahead. But, and also those are not going to be enough for global encryption. If we want to basically build a network of global encryption around the world, we would need to have a way of communicating within different countries. We would need to have a way of communicating within different continents, you know, and that is way more than 500, 600 kilometers. And we would need some kind of relay system, such as the satellite constellations that we use at the moment to do telecom communication. So that is where space QKD basically comes in. Oh, so here you have the Loch Ness Monster as the eavesdropper who is trying to basically find what information Alice is sending to Bob, what is the information encoded in the key. So if basically our dear Nessie wants to eavesdrop on the photons, then she would have to alter the state of the photon because it's a quantum particle. And so you will always, Nessie is always going to input a level of error into the raw key that Alice is sending to Bob. And this is the level of error that we calculate at the end of our post-processing to figure out whether this key that we have sent is secure enough to use or whether somebody has gotten too much information out of it. There is a threshold, which is known as a qubit, right? And so if we find that a key has been compromised, we can just discard the key and then start again. So this provides us always a future-proof security, even if a quantum computer is the one being used to eavesdrop, that we will always know, we will always find a trace of somebody trying to eavesdrop and taking away information. So right now, let's say that we have, I'm in the UK, many of you are in India, and so we want to lay a intercontinental, intercountry quantum key distribution network. So what we are going to be doing is we cannot use terrestrial QKD here, as I just mentioned. So we can come to an agreement, and let's say that we set up two different ground stations, one here and one over there. And we'll come to an agreement and send a common satellite up. And it depends on our agreement, what kind of a satellite it's going to be, what orbit is going to be, how many keys do we require to communicate on a daily basis or on a monthly basis or a yearly basis, and what purpose we're going to be using these keys for. But essentially, what it's going to be doing is the satellite is going to be used as a trusted node, as a trusted relay between these two ground stations to basically relay the key. So the satellite, first of all, we come on top of one of the ground stations. So let's say it comes on top of me. It basically opens this quantum channel, which looks very sci-fi-ish, I know, and that's super cool, I find. And then it goes over to the other ground station over in India, and then it will open a quantum channel when it's there in orbit on top of that other ground station. Now, if we choose the orbit such that this is a 500 to 600 kilometers low Earth orbit, then we're kind of within the bounds of what terrestrial QKD was doing. But the difference here is that the photons are going to be traveling most of the time in free space, in vacuum. So there is no atmosphere to introduce a lot of loss into the channel, right? And at the end of that, they will be going through atmosphere of around 10 to 20 kilometers at the most. So we mitigate a lot of the problems around long distance quantum key distribution communication. So you have to, that terrestrial communications face in quantum. And by using such a satellite, by using such an orbit. Now, this is where complexities start adding up. Because we're going to be quantum key distribution demonstration in the world that was done by MICEUS in China. And MICEUS was a very, very big satellite. It was a conventional satellite. Conventional satellites like that basically take large teams like ISRO or NASA or the Chinese Space Center, the Canadian Space Center, anyone like that who have in their disposal a large amount of money. And they can absorb a lot of the risk because you're only going to be able to send up one big satellite every few years because it takes time to manufacture a really big satellite. But the good thing about using a big satellite is that you will be able to put a large optics table inside a satellite, and you would not have to find innovative manners of making everything smaller and smaller and smaller to fit into it. But the problem is, if you want to use a large satellite, then that requires, again, as I was saying, big teams, but also it's not faster. You would not be able to send up many, many, many satellite constellations to cover the globe or even cover a part of the globe. In order to do that, the solution is to go towards something which are known as Cubesats or nanosatellites. Now, these nanosatellites are extremely small, and they were invented as a way of letting university students get some hands-on training by building actual satellites in Stanford. And very soon it was found out that, hey, these little satellites, these cute little satellites, which we can send up really fast, they cost less than 1 to 2 million if you have like actual payloads on those satellites, 1 to 2 million pounds, I should say, per mission. And that is a reasonable amount of money. That's actually a small pot of money for a government to spend, for example. That allows multiple different companies, that allows universities, that allows governments also to send up really small satellites very fast using smaller and more dynamic teams. So you can take really quick decisions, and you also have a larger risk appetite, because let's say one of your satellites, something goes wrong, then you still have a big pot of money for other satellites that you can send up, right? So, but the complexity again becomes much bigger because you have to take a huge, big optics table, and then you have to miniaturize that, I don't know, like 10, 20, 30 times to make it something which fits on the top of my palm, and which is extremely small, extremely robust, because again, smaller satellites are launched as a secondary payload on bigger launchers. So they are kind of exposed to a lot of vibration, extreme amount of vibration. And so when you're using optics, you have to be extra careful, and that's super difficult, because these are glass and other kind of materials which are going to break in a vibrational environment, right? And there exists another kind of problem in satellite QKD as well. The problem is that because the beams are so weak, especially in single photon QKD, because single photon sources are super hard to make, and there are a few companies around the world trying to make true single photon sources. They're not yet practically usable. So what most of us do when we do single photon QKD is that we do something known as weak coherent pulse laser quantum key distribution. And what that means is that we use coherent lasers on board a satellite, and then we attenuate the output of that laser a lot, so that effectively each pulse of that laser gives us 1 or less than 1 photon on average. And this is how we ensure that we're getting single photon QKD approximation. Now, the problem is that these are very weak signals, and they have to go through vacuum, and then they have to go through atmosphere. There will be a lot of atmosphere and weather conditions. It would lead to beam wandering everywhere. So you'll have to figure out, how do we effectively collect those weak signals? And a big problem comes in when there is cloud cover on top of ground station, because that is a lot of obstruction. And unfortunately for us in Scotland, it always rains. There's always cloud cover. And so that's terrible. What is a way of going around that problem is a big question. And this is also a big blocker for governments adopting quantum key distribution as an encryption method, because you cannot always wait for cloud to go away. And then you'll have to match up the orbital schedule with the cloud schedule, which then adds up more complexity into it. So we need to find an innovative solution to get around that cloud cover problem, right? So remember that, because we'll come back to that later. So on top of that, basically, we will need to fit into a satellite a small quantum source. We will need to actually onboard other quantum stuff, such as a quantum random number generator, because for any cryptographic system to work securely, it bases itself on the randomness of random numbers that it uses to generate quite a lot of the keys. These random number generators do not always provide true random numbers, because a lot of our random number generators are based on the electronic noise of systems, which are quite random, but there is a chance that we would be able to detect or predict them using really, really clever algorithms or computers or something like that. Now, quantum random number generators basically they're quite a different variety of random number generators, because they use, again, quantum mechanics, and they're quite different ways you can produce a quantum random number generator. And we have been in another project taking in various different commercial quantum random number generators that are already in the market, and then testing them out to see whether they are good enough to be onboarded onto a satellite environment, first of all. And second of all, whether the randomness, the output of those random number generators, the random numbers that comes out of them, are they, again, good enough? Are they random enough? Are they truly random? So in order to do that, you can use a lot of statistical suites and statistical tests like die-hard testing or small crush and big crush and alphabet. And we work with National Physical Laboratory here in the UK to get their expertise in analysis of these random number outputs and then see, okay, we have a high confidence in the random number that are coming out of this QRNG. Only at the end of that would we be able to justify using that QRNG for a QKD system. Now, again, you have to make the QRNG smaller. You also have to make the generation of the quantum random numbers quite fast to keep up with the rates of your quantum key distribution system. And we'll come to that again in a little bit of time. There will be other problems like when the satellite is going over the ground station, the satellite can rotate a little bit. So how do we make sure that the polarization that the satellite is transmitting is exactly the same as the ground station is receiving? How do we post-process that? How do we make sure that we correct for the beam wander, for example, that happens when it goes through the atmosphere and diffracts? How do we, what is the size of the telescope aperture? What is the size of the telescope aperture, both on the satellite as well as the ground station, for us to have the maximum key rates and the minimum losses? And then the satellite also has an inbuilt pointing error. And we'll have to make sure that the beams that are going up from the ground station and coming down from the satellite kind of form a handshake so that they are on top of each other in order to find each other. So that, again, adds more complexity. So on and on and on, right? And again, this slide just kind of summarizes the advantages and challenges of space quantum comms. So the advantages that we will have a longer range, more accessibility. We can provide keys to remote environments, like if you're on an oil rig somewhere in the middle of the sea, then yes, satellite will be able to go up there. No terrestrial network will be able to provide secure quantum keys over there. It will be able to take, I guess, we can use optical fibers. I guess we can mitigate the shortcomings of optical fibers here, and using intersatellite comms, we will be in the future should be able to do maybe satellite to satellite transmission as well and receiving, and that is known as intersatellite communications, and we will be able to provide global coverage. Challenges is that there is a big cost of access to space. Even though CubeSats are smaller and cheaper, there is still a big cost of access to space. And this is what people mean when they say the space is getting more democratized at the moment, because we're using small sats and CubeSats, and UK at the moment is, I think, building the first ever small satellite launcher in the world, like dedicated to small satellites. We are making it more democratized so that everybody can get in on this, but we're still not there where they're actually, cheap in many people's relative terms. Another challenge, we would not be able to do daylight operations at the moment because, again, these are weak signals. They are susceptible to quite a lot of background light noise. And so we do nighttime quantum key distribution. And as I was mentioning, there are technological challenges around miniaturization, making sure that all the systems are space hardy. Then there's obviously the timeline of space missions, like you have an orbital life cycle. I need to make sure that all your instruments kind of will survive throughout that orbital life cycle. You need to track whether your instruments are degrading during those life cycles, and you need to put in place proper precautions for all of that. But you can see that basically the satellite to ground link efficiency is like over there, all the way top of there. So the link efficiency is quite high. In higher distances, it does not go down, while ground telecom fiber efficiencies go down quite steeply. That is the biggest motivation towards going towards space QKD. And basically, this is what like a final space QKD network will look like. You will have a network A, you will have a network B, and you will have maybe, different satellites or one satellite going over both of them, and then having a final key shared between those two networks. And then this has to integrate between all of the existing ground station networks between all of that different buildings. So you would need some sort of a key management system, and then figure out what kind of authentication mechanism you will be using for those keys. How do you make sure that the person you want to send to is actually the person that you're sending it to? So there are some open problems in QKD at the moment, like authentication, for example. So we need to be solving those at the same time as well. So going back to industry, here's a snapshot of the numbers at the moment in the global satellite industry. It is worth around $271 billion. It is 73% of space economy at the moment. Cybercrime is worth around $6 trillion in 2021. So, and a lot of people have seen that data harvesting attacks are becoming more and more common. Now, what does data harvesting attacks mean? They mean that a lot of cybercrime syndicates are just attacking so that they can take your encrypted data and store them right now, but they would not be able to crack them because they don't have access to a commercial grade quantum computer right now, but they will have access to a commercial grade quantum computer starting 2027. So that is actually quite a big concern and something that we should be very wary about because the time to act is right now. Then we have the satellite quantum crypto economy, which is worth $254 million by 2024. And that is quite a big number as well. So we are seeing that we are on the trajectory where satellite quantum cryptography is making its way up the ladder, and people are more and more starting to accept that, yes, this is what we need for the future. To give you a little more perspective on Cubesats, what exactly are Cubesats? They are basically satellites which have their units as a 10 centimeter by 10 centimeter by 10 centimeter cube. This is called as a 1U cube, 10, 10, and 10. And you will be able to stack those cubes up in various different ways to form a bigger satellite space. So the typical satellites that I work with are 1U, 3U, 6U, and 12U. A lot of the satellite manufacturers have these satellite buses, which are basically a metal structure that looks like that. And they have various different standard interfaces. And also, that's another good thing about Cubesats. Like, because Cubesats are small, they are able to be standardized all over the world. And so all the systems that we develop for quantum key distribution will need to have, like, they already have some standards to kind of define their interfaces towards, converge the interfaces towards these kind of standards, right? And I've just put like a really big loaf of bread to give you a scale of how small these things are. Actually, like a 6U satellite would be kind of like that, a little bit bigger than that, actually. Maybe I should change that. But yeah, they're not too big. They're kind of like a very big cereal box. Like a Kellogg cereal box, for example. This slide is kind of an overview of just what I was mentioning before. Cybercrime and gray zone operations are becoming increasingly prevalent. Space-based quantum technologies were discussed at the G7, and that means that there are quite a large number of new missions and players there now. Current QKD developments seem likely to lead to complex multi-domain service delivery. So what does that mean? We will need to figure out how do we deliver keys to aircrafts? How do we deliver keys to ships? How do we deliver keys to various different telecommunication networks that are already on the ground right now? So it's very multi-domain. It's very multidisciplinary as well, and it will be very cross-industry. So finance industry, health industry, service industry, telecommunication industry, all of those kind of things. So Craft Prospect, which is my company, they're developing nanosatellite delivered quantum key distribution services to augment the other ground and space networks that are rolling out across the world in quantum key distributions. An example of this is we got our first in-orbit demonstration mission ROCKS, which we are working towards, and the launch is next year. This is a 6U CubeSat, and this combines cloud-sensitive quantum key distribution technology with our responsive ops products. What that means is this combines that with our artificial intelligence products to deliver global service capabilities for secure telecoms. We got awarded £1 million in kind through Satellite Applications Catapult and the UK Space Agency. to a total mission cost of around 2 to 3 millions by the end of next year, and that's when launch is going to be. We work with our partners at University of Bristol, University of Strathclyde. We're talking to service providers such as British Telecoms, for example. They're a telecom company, and they are already doing QKD terrestrial testing in their telecommunication systems, along with other companies like Toshiba. So we are talking to them, and we have been in projects with them to look at the feasibility of rolling out satellite quantum key distribution as a service after Responsible Operation for Key Services mission, ROCKS, is already launched. So what does quantum in a CubeSat look like, right? So for ROCKS, it kind of looks like this. So in order to get beyond the cloud cover problem, we have artificial intelligence on the satellite. So we use neural networks which are hooked up to imaging systems. So we will have a hyperspectral camera on the satellite. The camera will switch on before the satellite goes over the ground station. So just when the satellite is coming up on the horizon, and the camera kind of can see the ground station in the future, 4 minutes to 5 minutes before it switches on, it takes pictures of the suborbital environment and above the ground station to see if there is clouds. It takes a lot of pictures. It uses neural networks to do cloud classification, image classification. So it needs to be able to do nighttime cloud detection because we are using QKD during the nighttime. These neural networks, then after they classify, they go through a classification mechanism and they say, okay, 99% accuracy, there are clouds over this ground station, something like that. If there is clouds, then we decide that we would not be able to deliver a key. So the artificial intelligence also has to do quite smart decision making. So it has to be like, no, not this ground station. It will need to be having access to geolocation and georeferencing data to basically look at where other ground stations are in the same area. And then it will need to send a communication to the secure computer on the satellite to tell it to point the satellite in a different direction over to a ground station which actually is free of cloud cover or not too much cloud cover. So obviously all of that information is then processed through the electronics layer, and the secure computer, once it's making sure that you have the line of sight between the ground station and a satellite, it turns on the quantum random number generator. The quantum random number generator then churns out a large number of quantum random numbers. These random numbers then decide which laser drivers are going to switch on. So we have 4 laser drivers on board, and each of the laser drivers can basically drive 2 different states because we're doing decoy state quantum key distribution. So basically we will have 2 different intensities of pulses that can come out of all of the 4 lasers. And each of the lasers spits out 1 pulse in a particular polarization. So either a horizontal polarization, the second laser will spit out a vertical polarization, the third one is capable to spit out diagonal polarization, and the other one anti-diagonal polarization. And then the order that these are switched on, so like pulse, 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 but then you want to go H, V, D, A, H, D, A, V, 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 something like that, so that it's a completely random sequence. And that is where the quantum random number generator is very important. Now the laser drivers then switch on the lasers, it spits out all the pulses, goes through the optical paths, which has a lot of optics. It has a lot of lenses, collimators, mirrors. It gets pointed through a telescope on board the CubeSat and then goes into the ground to the ground station where it gets received. And then you will have a second classical communication channel between the ground station and the satellite to do all the post-processing and the reconciliation. So this is a snapshot of the company. And essentially, like for the last 4 to 5 years, we've been doing quite a lot of mission architecture, which means that we act as a systems integrator for small satellite missions. So what that means is that we basically help various different stakeholders, like universities, governments, different companies, service providers, payload providers, people who build satellites, people who build payloads, design their constellations. Like, what is the best design for a constellation? What is the risk analysis? What is the cost benefit analysis? All of that. And then you get a final mission design. That basically generated a lot of revenue for us, which we invested into developing our technology verticals, which are artificial intelligence and quantum tech. In artificial intelligence, our most mature product is the cloud detection algorithm, which is on an ESA grade European Space Agency hardware, ESA grade hardware, like an FPGA. And it is hooked up to a camera, which you can see there, over there. So that's known as a forward-looking imager, or the FLY for short, which is quite nice because it's going to be flying on the satellite. In the quantum tech vertical, we basically have quantum key distribution as our first and most mature products. And then it also feeds into the responsive operations, which is like decision-making on the satellite in a responsive manner. We were founded early to 2017 by Steve Greenland, who sent up Scotland's first ever satellite, which was actually UK's first ever Cubesat. He was also involved in some of the quantum and space small satellite missions in Japan, in Singapore, and then he went back to Glasgow and founded Craft Prospect. The company has grown quite well every year, almost doubled both in capacity as well as revenue, which is nice to see. And we've been working with quite a lot of these organizations on the right-hand side. And our core capabilities are quantum tech and optics, onboard intelligence, mission architecture, embedded systems like firmware, spacecraft operations, and we use something known as model-based systems engineering, which provides a more robust way of designing these kind of constellations, whether they are artificial intelligence or quantum constellations. So we bring all of these together to deliver on satellite QKD. So the vision for the future is that we would have a complex capability rollout, which requires a diverse supply chain offering for opportunities to augment quantum technologies. We use nanosatellites because they can perform critical niche services like fill gaps somewhere. For example, other providers might be sending big satellites up, but they have a certain area where they do not have any satellites. So you would be able to send up really fast these small satellites to fill up the gaps there, or lower value areas, for example, with low coverage. Our use of artificial intelligence can aid with cloud avoidance, for example. Technologies which treat the host platform as untrusted, like the satellite as untrusted, will be where we are going to be looking at in the future. But at the moment, the satellite is a trusted node. So we'll have to trust the security of that satellite. And so we spend a lot of time and energy and finances into making sure that all of our security supply chain is very robust, because a service is only as secure as its least secure element. If there is one weak link, we will all go down, basically. So this is a global satellite QKD timeline, or actually this is maybe, so I guess like in 2020, a lot of demo missions were being planned around the world. One of that is ROCKS. There are a couple of other ones, like India has its own mission planned. Singapore has a mission planned next year. There's a German mission which just went up, but I'm not sure whether it was just optical or quantum key distribution, actually. The US has its first mission coming up as well. And these are all kind of like similar scale missions, like they use Cubesats mostly. Canadian Space Agency, in collaboration with Honeywell and University of Waterloo, also have a space mission coming up called Qsat. And that is going to be actually a much bigger platform. But we are providing them a quantum key distribution source because they were using entangled proton QKD. And because our source is quite small, because it's built for a Cubesat, so it can very easily be used as a secondary payload. So they will be putting our source on their satellite as well. And we are also talking to a couple of other missions around the world where we can deliver our sources into. By 2025, people want to be targeting increased key generation rates, figure out how do we integrate quantum key distribution into existing terminals around the world. How do we make even smaller space and ground terminals? By 2030, we want to go towards daylight operations, maybe figure out a very good way of penetrating light cloud cover instead of going around cloud cover as we do at the moment using artificial intelligence. We want to be deploying smaller mobile ground terminals again, and obviously go towards even higher key generation rates. And by 2035, hopefully we will go towards having untrusted nodes, like satellites as untrusted nodes, and mega constellations around the world, and start feeding into our dream of having a quantum internet. And along this journey, we will need many different kinds of industries to come together to develop enabling technologies such as compact single photon sources, compact detectors, integrated modular optics, modular and low size, weight, and power kind of instruments, much better pointing technologies than we have currently for small satellites, and hopefully quantum repeaters as well when we go towards developing this global ecosystem. So just to show you what that miniaturization process looked like, this was the very this was like a year ago. So we took this optics table from the University of Bristol, and we miniaturized quite heavily, and then we had something like this box, which basically is less than 1U and can fit on my palm. So you can see a lot of the optical elements here already integrated. So we have some dichroic mirrors. That was actually one of the older quantum sources we had designed. It's quite small, as you can see. We have some mirrors here, which are like micro mirrors, and these are motorized. So you will be able to control the movement of the mirror. And this is super important because we need to be able to have a mechanism to point the light beam directly at the right point of the ground station. So this provides fine pointing, while the telescope is going to provide some coarse pointing as well. And the telescope is going to be here interfacing with this box. So that was just a snapshot of Appetite, which is the beam steering system. So Appetite stands for Acquisition, Pointing, and Tracking in Tiny Environments, and that this is the current version because we've already gone to like flight model manufacturing. So when you're trying to build something for a space mission, you kind of go through multiple stages. So first we did feasibility studies, which looked at how can we do this best? Next, we started doing engineering models. So all of that were like done on breadboards, and they were not tested for space. They were like, let's first do a very small, but the minimum viable product kind of a, concept. And then we went through another round of making a better engineering model, EM version 2, and then we went to flight model manufacturing, which is ongoing now. And that's what Appetite looks like. This has the control loop mechanism that I was telling you about, and it has the capacity to handle multiple lasers or beams for both the transmitter and the receiver beam path alignment. And you can see it has like certain boards over there integrated into it as well. This is the latest version of the quantum source. It's known as JADE. It stands for Joint Alignment Diode and Emitter. So this has the laser drivers and the lasers, as well as the alignment laser, which allows us to align all the optics in there. And it emits all of that through a fiber coupler here. The fiber then goes into Appetite. And then Appetite is completely free space. So the light beam just go inside of there without any fiber. And then that goes directed into the Cubesat telescope, which is known as Garnet. I forgot what the full form of Garnet was. I always keep forgetting that. It's a big challenge keeping up with all the different acronyms. So I apologize. But basically, we found that we were starting to look at, can we actually just buy something off the shelf? Can we just find a super cheap telescope, for example, or even if a telescope costs a little bit more, and just buy it and just integrate, make like minimal adjustments and integrate it into our platform. But we found that for the wavelengths requirement we had, for the apertures we needed, the length of all of these telescopes that were already available in the industry was actually quite big, and they would not be able to fit into the amount of space we had on a Cubesat. And so we have developed this, we're manufacturing this in collaboration with Fraunhofer, which is a research-based organization. So they help us design the optical, do the optical design, and we give them all the space system requirements around it. And so together we manufacture the telescope, which is again very small and very high performance. And the telescope needed to be made athermal because when the satellite is going in orbit, it'll go through really a lot of like cold and hot environments over and over again. So you have to make sure that your optics are robust against that kind of temperature fluctuation, extreme temperature fluctuation. So it could be, -40 to like +80 Celsius. And then we have an onboard payload computer, which is a high-performance Linux-based computing subsystem on a Xilinx Zinc 7000 platform. It will take care to make sure that the security of the whole system on board is taken care of, and to store the keys, to delete the keys, all of those kind of things as well, and to drive the decision-making of the artificial intelligence as well as the quantum key distribution. This is just a little bit, these slides are just a little bit more on the telescopes and all the different products, all the different products that basically go into that satellite together. So all of that is going to fit into a 6U Cubesat quite compactly. And this is what it looks like when you're trying to make everything fit into like so this is more like a 1U, this is a 1U Cubesat, the top of it, and they're just bringing it down. Over all the different layers that you have. So you would have like Cubesat computer modes, you will have a lot of the software and protocol layer, which will be on the boards here. You would have a lot of embedded systems, again, more boards. You'll have electrical and other hardware, and then you would have like optics, lasers, LEDs, mirrors, telescopes as well. This slide just gives you a snapshot of the payload box in comparison to the satellite bus. So that's what an actual satellite bus looks like. And so it's also quite small, and the payload box is quite small in relation to that one. So all over the world right now, there's quite a few different QKD in space missions upcoming, and here it kind of tries to capture examples of various different technical approaches. So Spectre, for example, which is a RAL space mission that uses the entangled photon QKD. As Urvashi was mentioning, they are developing entangled QKD as well. We are doing a single photon. Qsat will have both single photon and entangled photons. And, there's a lot of MICEUS follow-ons, which are also, done. And this is where we have Quark, which was the pre-ROCs, and then we have ROCs coming up next year. I think these kind of go into a bit too much detail into the considerations of the Cubesat making, so I'm going to skip those ones. But what is important at the end is to understand that we need to do secure space systems testing. So that, as again, Dr. Urvashi was saying, that we will have to align to standards all over the world. So we do quite thorough, checking to ensure that we have done a lot of security testings like tempest testing, penetration testing, threat modeling, space-based testing, incident response, and so on. You also have to do like the theory testing. So we have academics from University of Strathclyde doing that side of things. We have cybersecurity professionals from the cybersecurity industry, and we are quite compliant with the ETSI standards testing, which is ETSI is like the hub in the EU, basically Europe, for satellite QKD standards, and be a part of that. And we make sure that we basically provide like a compliance metric at the end of a commercial development of the system when we are handing it over to a customer. And then we obviously have to look at hardware-based security as well, and the security of the random numbers. So it's a complex system. There will be a lot of stuff that we will have to take care, and we will have to evaluate quite a lot of different kinds of security. And obviously there are problems because we are using quite a lot of commercial off-the-shelf components because we just buy them off the shelf, which are industrial grade or commercial grade available on the market. And we are not sure what kind of security they have inside. So we have to make sure that there's security of open source systems, and we can upload security patches when the satellite is online. Again, this is just a snapshot of ROCs and all of the different things that goes into ROCs. So this is what the actual satellite is going to look like. This is a CAD model. So that's where the quantum key laser source is going to sit, the jade green one. That's going to be the appetite, the beam steering, that's the telescope. That's this one is a fly, and that one is some other stuff, I think. The secure quantum computing, I guess. And then you would have some other star trackers and stuff that the satellite provider wants to put there on board. And so basically, you will be bringing everything together into a 6U cloud-sensitive quantum key distribution satellite and cover them with solar panels and everything that requires the satellites to be in orbit. And we will deploy that to augment future cybersecurity by ROCs in 2022. So I think this is where I will stop now. So thanks very much again for the invitation and for listening to me. And I will be happy to take any questions. Thank you.
Thank you very much, ma'am. I would request the participants, if you have any questions, please raise your hand.
Samyukta, I think you have raised your hand. If you have any queries,
I have one question.
Yes,
Is there any
yes.
protection against jamming, that is the ground station or the satellite?
That's a very good question. At the moment, there is no protection against jamming, but we are looking into funding a project which is going to look at the usage of artificial intelligence again to detecting jamming signals on top of a ground station. But at the moment, we would want to build in resiliency if we have a constellation. So you would want different kinds of platforms at different kinds of altitudes, so that if one particular thing is maybe jammed, then you would be able to, like, send to a different ground station maybe, or from a different layer on the atmosphere.
Thank you. Thank you.
Welcome.
Question?
Yeah.
Can I ask
Yes.
the question?
Yeah.
Please,
Am I
ma'am.
audible? Oh,
Yes,
that was
yes.
very nice talk, if I may, Sonali. You have talked about Cubesat. So now question would be that, of course, Qsat is meant for a larger mission, right? Larger satellite, and the
Yeah.
entire talk was on the Cubesat. So now, how do you see the complexity changing when we go from Cubesat to nano to micro?
Right. So we are able to kind of make our interfaces customizable. So even though so at the moment we are producing two different quantum sources. So one is for ROCs and one is for Cubesat. They are mostly the same. One is for ROCs and one is for Qsat, which is is not a Cubesat. Yeah. So they're mostly the same, except that our Canadian partners wanted the quantum source to be externally driven. So and on ROCs we will do it internally. Because we have control over ROCs. So we have made that quite customizable, so it can be externally driven or internally driven as well. We have made the interfaces slightly different as well, but we did not see that much of a difference going between Cubesats and as a secondary payload on a microsatellite like Qsat, for example. And nanosatellites are much easier.
But then you're talking from the source perspective, but then we have all these modules, right, which we have to worry about when we're going to do this. So then in that sense, for instance, the other module where you're doing pointing and tracking. So that is also, of course, at the Cubesat level that we had the discussion today from you. And so there, of course, it may not be a trivial extension.
Yeah,
right?
I think that'll be a much bigger extension than the source, definitely.
Right.
But yeah, we are not doing that at the moment, so I don't think I have much insight into how much of that change is going to be necessary.
Right. Thanks a lot. Yeah.
Welcome.
Samyukta, ma'am, can unmute yourself and ask the question.
Yeah, please go ahead.
I think she has dropped out of the call.
Yeah, sorry, I'm unable to see all the participants. So if somebody has their hands up, if you can just speak up, that'd be great.
Yeah, Sonali, thank you very much for accepting. It was interesting and wonderful. So I have got one question about, so you see this Cubesat is very miniaturized, and I think you may face some computational issues when you do a classical post-processing stuff. Very difficult for handle a large amount of payload in the transmitter. How do you handle that, or is there any other mechanisms where you can do this parallel?
Yeah, we do a lot of compression on the data that we downlink down, to the ground station, and hopefully we'll be able to like use the X1 band as well. So, and that's currently we are looking into it. But yeah, there will be a significant amount of data compression, because yeah, we'll have to go within the limits of what is available on board, and that's not as much. But the good part of is that because there's so much limitations, it kind of also pushes us to think think out of the box and drive innovation a bit more as well. So that's nice. Are there any more questions?
Yeah.
I think there's
Syrac. One more. Yeah, there's one more.
Syrac.
I just would like to know the key generation rate in case of satellite-based QKD. How do you compare with the other key generation techniques? The rate at which you generate the key.
Sorry, can you repeat that again?
The rate at which you generate the secret key in the QKD system based on satellite to the fiber optic cable. So what kind of a comparison?
That's actually a very good question. So our QKD, the raw key or the frequency of the source is 100 kilohertz to 200 kilohertz at the moment. It is probably much lesser than what terrestrial QKD systems have right now, because that's quite mature. Let me look that up quite fun, because I've forgotten what is the state of the art.
Yeah, maybe of the order of a few bits or kilobits, kind of. Just a range of.
So key generation rate. So we will be able to provide 10,000 256 bits keys per year with ROCs.
Thank you.
Welcome. Is there any other questions? Like, all the questions have been super insightful and super good. So thank you very much for that. Really appreciate it.
Thank you, Sonali. Wonderful talk and covering various aspects of satellite-based QKD and also giving the industry perspective and industry, the state of the art thing. It's really, wonderful presentation too. I do hope that we can share these slides to the audience.
Yeah, I'm gonna just check that if I haven't not included any confidential ones, and then I can definitely send that over.
You can send it to Dr. Natarajan. So
yeah.
Thank you.
Yeah, and just to I guess note that obviously my experience is working in the UK industry space. I know that there's a lot of work happening about this in the Indian industry space as well. And I think we have been talking to some people. I don't exactly know who my team has been talking to, but from generally what I have seen, the industry space kind of develops in the same kind of manner. And it's, I guess, nice to have that cross collaboration and see what is going on everywhere in different countries, for example, and what works where, what doesn't work where. It will be quite different depending on where we are building something.
True. Thank you. We will take it further. Yeah, this is just a beginning with you, and we continue. Thank you.
Thank you very much, ma'am, for an insightful talk. Means, as Syrac sir mentioned, means getting an industry perspective. You pointed out issues in long distance QKD, the cloud cover issue, how AI can be used to solve that, the sizing issue when we come to satellite based QKD, the miniaturization aspects, the instrument degrading with orbital life cycle, etc. So these are the things when we start in quantum communication, we are more worried about the protocols, but when we look at practical implementations, these are something which will need some serious discussion and brainstorming. Thank you very much, ma'am. With that, we will.
No problem.
With that, we'll move to the third session, that is practical challenges in quantum networks and solution. For that, we have Dr. Natarajan who's currently with SETS Chennai as scientist and has worked in the domain of cybersecurity for nearly 12 years now. His research interests include secure quantum communications, experimental quantum key distribution systems, applied quantum cryptography, etc. So I would request Dr. Natarajan to please take forward the session. Thank you.
Thanks, Vaibhav. Good evening, one and all. So good to have you all here this evening. So in this talk, I'm going to cover on the kind of a computer science perspective of how this quantum network looks and what are the different challenges that we face when you try to implement and realize these quantum networks when you're enjoying it in the field. So I'm just quickly going through the little bit history of where this quantum revolution starts. It basically all of handling data from the different sources. When you say in the beginning of 19th century, the data it is processed with the transistors, and then it moved to hard disk, and then electromagnetic hard disk, and then followed by laser. Now we are in the end of 20th century and the beginning of 21st century. We have now single photon technology. So before we go this single photon technology, if you look at the overall perspective, how this quantum technology covers is it's basically a hybrid domain which combines physics, math, and computer science. And this single photon technology is like it not only in communication, it is been penetrated in across all the technology world. So before that, how these three science been bundled together make this wonder happens. So I'd like to quote a funny story by Richard Feynman. So there was a team of scientists were discussing physicists and math and computer scientists. So these three were discussing, and this was a motivation example which was given by the Richard Feynman, which Nobel Prize scientist. So physicists and mathematicians, computer science were discussing about which is best. As option is a girlfriend or wife. So the physicist says, girlfriend, we can do experiments. And the mathematician said, wife is more secure. Then finally, computer science says, both are okay, because either girlfriend or wife, it creates problem if you're not handling properly. So it is a funny example quoted by Richard Feynman, but it has a deep understanding. I think you all know how it explained. So the reason is it should all combine cohere together, which makes this quantum technology happens. So that's where the single photon technology comes into picture, where these different form of informations can be encoded and decoded in a secure way so that it can be used for different purposes. But in this talk, I'm going to cover of only a quantum network perspective, how this information been encoded and decoded and used for different information sharing. So a single photon is a carrier of carrying information, but it transmitting a single photon to one end to another end. Then we can make a different sort of measurements. So the difference between a classical and a quantum is a classical works in a two different states, either on or off, but in a quantum, it is a combination of two. So if you look at the diagram here, it explains how the single photon works. So here, if you see a graphical representation of an empty box, which is represented as 0 bit, and one is full of shaded 1 bit, and mixture of these two as a qubit, right? It's a combination of two. So basically, it takes a single qubit to carry two different classical informations. So this is a beauty of quantum qubit, which gives more tremendous applications in computing as well as communication. So and for that, we have a nice encoding decoding tables, which is provided by Stephen Weisner, how that needs to be encoded. The qubit needs to be encoded with the classical bits. Then the classical bit can be transformed in a qubit version. So for that, we use a basic kind of called a basis. This basis we will be explaining in the next slides. Okay. So before that, I just want to make it clear how different this quantum information with the classical information. So in 1940s, Shannon proposed an idea where information can be represented as bits. It's a logical form of bits, zeros and ones, and then these zeros and ones can do all wonders. Right? So till date, we are in the mindset that zeros and ones can be operated with bits and bytes with the different software applications or devices, and it's been used. But at the same time, law of Landau is explained. Information is no more logical, it is a physical phenomenon because this information is stored somewhere in a physical medium and it's purely a physical process. So that's where these the quantum things comes, I believe, because every information we are trying to handle, it has physical behavior, right? So that physical behavior is going to exploit in this quantum space. Where in classical phase, we only concentrate on the logical aspects of the information. We don't bother about the hardware layer because we have information in bits and we operate everything on bits. Whatever algorithm we use, applications, everything on bits. But here we are going down another approach where why can't we exhibit some of the physical behaviors of the information? So wherein everything is a shift from one domain to another domain. So let's be 2-3 slides of basics of quantum mechanics in a computer science perspective. So there are two. Here is you would have heard of a term called measurements. People where in a classical sense we use to count the lengths because it's all discrete phenomena. We just count the rates and bit lengths and so on. Here we usually call you, if you look at the papers, the term measurements because it's all pulses. All qubit is a single photon. The single photon behaves like a pulse. Then that pulse is measured with a certain set of measurement equipments where since it's a continuous phenomenon. So these are like, and I also want to remind that since we are trying to exhibit physical behavior of a qubit or photon, then we need to study a little bit of mechanical aspects of quantum. So that's where these two basis concepts come in. So this is used as a measurement basis where you can filter out. This is basically a filters which filters the photons in a certain orientation, and then it exhibits what qubit representation is based on the encoding table that I've seen. Right, and typically the measurement looks like this. If it's like it has 4 orientations. One is a horizontal and vertical and diagonal, anti-diagonal, wherein it's combined with horizontal and vertical is one basis and anti-diagonal and diagonal is another basis. These are two filters which used to measure these qubits and transform it to decode it as information. So this typically this measurements looks like this. A horizontal photon comes to the measurement equipment and it tries to measure whether it is 0 or 1. Right? Straightforward. When you apply a wrong filter, then it takes 50% chance it's trying to predict as a 0 and a 50% chance to predict as a 1. So if you apply a right basis choice and right measurement, it will give a right results. That's we have some security properties oriented that I'll be explaining it in a couple of slides. So some of the operations I just highlighted, C0, Hadamard. It's basically in terms of mathematics, this is a complex field under a Hilbert space. All the operations that we perform, it bound to the vector space. So that's where the unitary operations and the tensor products are used, and these Hermitian kind of transformations where transforming one state to another state. Well, So the next is, I would like to mention two important principles of the quantum information. One is the no cloning theorem, and another one is the uncertainty principle. So no cloning theorem states that you cannot clone this quantum information, or you cannot copy the quantum information. Whereas in a classical world, you are making a multiple copies of data, and you make you have a fantasy of creating a mirror of image or a VPN connection. So many things. You just make it a multiple of informations. But here we have a restrictions to make a copy of information. So this cloning, no cloning theorem is explained with this simple example. For example, two kids want the same apple. So the same apple is same apple, where it is the same weight, same color, and same taste. Everything's right identical. So it's very difficult to hard to find out the one such apple. Like even if you go to the tree that produce that apple, you cannot get that similar one or identical one. The reason is this apple is produced by nature, and all according to the philosophy, all the objects which are produced by nature is identical, right? That you cannot clone, or there is no physical process exists to clone kind of a object. See, this is a very important security property that being utilized by this no cloning theorem. You cannot copy a qubit or photon because it's produced. It is a nature source. Right. So that's where all the operations in the quantum are linear operations. There is no non-linear. The copying operations is not allowed. So if you look at the equation here, you can perform allowed to perform operations like with different elements, but you cannot create a copy of. So this kind of a non-linear operations are not allowed. This is one important property of security. So another one is an uncertainty principle, where this is another important principle where you cannot measure position and momentum of a quantum particle simultaneously. So this is another important, very important principle where you cannot to convert this into a basis form. You cannot apply same basis at a time to figure out which photon, because it's an unknown photon, unknown pulse. You cannot apply both the basis on the same time to identify or measure these photons. For example, if you take so let's say you have a quantum car with GPS, but you're driving at certain speed. When you try to compute, identify the locate you, where are you if you are driving a quantum car, it's very difficult because you cannot measure the speed of the car and the location simultaneously, because it holds a quantum property, right? So the momentum is different and the location is different. That's a very important quantum property where when the quantum information flies, the qubit flies, it's very hard to identify the unknown qubits, what state it is. Okay, so this motivates us to proceed with quantum safe communication, where the conventional systems will not guarantee that physical security, and even a private channel in our conventional networks, which may not give guarantee that it is not known to Eve or because the sender and receiver may not have a knowledge whether someone reads that particular information. For example, if you see these properties of a physical object, for example, if you have a paper document or magnetic tape or a USB stick, so if you try to, someone is copying or reading your information, you may not be noticed that the information is read by someone, right? But the quantum cryptography or quantum technology offers a fundamentally different approach, which notifies the users where if the information is tracked or read by someone. So this is an important principle of quantum cryptography, where you can share a secret string using a quantum channel without knowing Eve's information. So that motivates the most of the symmetric key approaches in crypto systems. Next one, please. Yeah. So the quantum secure message exchange. So the quantum systems basically includes two channels. One is the classical and quantum channel. Quantum channel used for transmission of photon and classical channel used for authentication and key post-processing. So basically, this information is encoded and obtained by two different set of approaches. One is a non-orthogonal quantum states, which are single photons. Set of single photons were used to transmit secret bits or information. And another approach is entanglement-based approach, where you can entangle two elements, because the entanglement-based is well famous even in linear algebra. It's called linear combination of two elements, which behaves in the same vector space. So this entanglement-based approach also used to transmit the information with the same security. So as I mentioned, if some intruder inside the quantum channel, it is easily detectable. So according to the no cloning theorem, if cannot copy the states sent by the center, and if cannot measure both the bases simultaneously. So these are two important principles which enforces the security. So a resultant, it offers the unconditional security according to the laws of physics. Yes, let's come to a quantum network. So quantum network, it observes all the properties that the physics guarantees. It holds all the security properties and then try to share the quantum states from the remote nodes. The remote nodes is something from one user to another user. And it also offers, as I said, it unconditionally secure. And classical information can be encoded using qubits and transmitted to a remote users. And someone tried to copy the information, quantum information, or unauthorized users into the quantum channel, it destroys the information. And this will help us to identify the eavesdropping challenges in the quantum channel. So these are like a kind of a features that their quantum channel offers. Please. So how different from the classical systems to a quantum systems? So if you look at the differencing factor, the classical message are bits and quantum messages are qubit, where a classical communication is basically internet. It has conventional protocols running on top of it. We can get run all applications. Whereas in quantum communication, it's basically a super dense coding, where it's Qkd-based systems where quantum key distributions are used and encoding decoding principles being used. And also there is a quantum internet where the qubits are directly transferred from one end to another end, where the qubits being used. We'll discuss further how these communications internal aspects as well. And here, as I mentioned earlier, 2 bits of classical information being exchanged using a single qubit. Likewise, it reduces the operation as well. So single qubit is enough to exchange 2 bits of classical information. So if you look at the right-hand side diagram, so there is a clear indication of different layers being used in the typical OSI model. Here it starts from the physical layer and the different layers being used in a typical network. Whereas in a quantum networks, it has a physical layer like conventional, and it has an application layer. In between, there is a layer. It is a middle level layer called link layers. So basically, this is a data link layer. Here also, there is a link layer where how to generate the qubits via physical source and make it as a flying qubit and send it to one end from the other end. So there have been different mechanisms being used how to handle these flying qubits and send it to one end to other end. So one important principle is a entanglement-based principle, which is used for a concept of entanglement used widely in the networks. So there is this EPR is very famous. I hope you know that how this entanglement superposition principle works. 2 particles can be entangled together. It's basically a linear combination of 2 super. If you look at the equation here, it's two qubits be a pair of qubits be entangled together with the linear combinations. When if you perform a measurement on one side of a qubit, then you will be able to expose the other side. So this is an interesting property of entanglement based network. It's been used for transferring information from one end to another end. Okay. So quantum network structure, how typically the quantum networks basically works. So there are two types of networks models being exposed, but this is not there are many things exploring now. It's an exploration area. One is a switch-based network model. Another one is a trusted repeater-based network model. So switching-based is basically these all networks. The experimentalist trying to use our conventional networks or standard telecommunication networks and standards to implement this quantum network. And one is an switching based, where you can switch the networks from one to another, and you can change the wavelengths, other stuffs. And there is another important thing is a trusted repeater. It's a more famous model where you just repeat. Repeaters been used for long distance. You just replicate these qubits and send it to other end. So if you look at the diagram here, there are end nodes. These end nodes trying to start with some preparing qubits and sending it to, and these repeaters will take care of how to transfer, swap. There are methods how to entanglement swapping can happen from one end to other end. Or there are many mechanisms being used how to transfer the qubits from one end to another end. So if you look at the diagram here, there are two main principles being identified. One is the quantum repeater based, where you linking the entanglement pairs. So if you look at the diagram here, there is a Lace and Bob. So creating an entanglement pair, keep one copy here and send it to other one. So this repeaters basically linking these two via these EPR pair generators. So another one is a BSM. It's a Bell state measurement, where it's an alternative of EPR things, where you can use a entanglement-based swapping, where in end-to-end entanglement. So here is just create a pair and apply the Bell state measurements, where you can swap the entanglement states. So these two are important concepts where this entire quantum network being generated. So overall architecture of the quantum network and how it grows. So here it's a timeline and the functionality. And the functionality is being upgraded day and day, and then timeline also growing. Initially, this quantum network started with the trusted repeaters, where it's basically it acts as another quantum network node. So repeat, its name itself stands that it's either swaps or it creates an entanglement. Another one is a prepare and measure based networks, where you generate some bits and then it's so according to the BB84 scenarios, the prepare and measure networks fit into that. And there is an entanglement distribution, as I discussed. It used for metropolitan networks, where short range communications can be done with the entanglement based networks. Now it's moving to quantum memory networks and fault tolerant qubit networks and the quantum computing networks. It's aligned more to the functionality towards the quantum internet. So all the down three are it's partially dependent on the classical networks, classical systems, where it perform once it's performed the measurement, everything being post processing methods. But the top three is closely moving to a quantum internet, where it heavily depends on the quantum computing aspect. Maybe in quantum internet, where once the quantum computer available, then we can perform these kind of things, because we need to keep the memory of these things. Let's go on insights of quantum network stack. So as I mentioned, this is a kind of architecture that was created by PsiQuantum, and one of the papers they have mentioned how this quantum network stack looks like. So it's like a typical starts with the physical layer and the link layer and the network layer and transport layer and applications. So quantum device layer is responsible for creating quantum qubits, and it's a memory qubits, and then transfer it to a link layer. Then link layer is responsible for generating a flying qubits, it's a communication qubits, and then it goes for the network layer. So the network layer will pad it with the users and then distribute that. So transport layer, likewise, it takes care of a transport of qubits. It's typical network architecture, but there are many more physical activities that needs to be carried out. That is quantum mechanics that needs to be carried out in these link layers and the physical layer. So here I am highlighting some of the standard. This is a one such example. It's not the common diagram but I would like to explain how the internal works. It's basically the entanglement creation process is called heralding, mid-heralding process protocol, where these herald photons can be generated here using this physical layer and then send it to the scheduler. Because this link layer and physical layer are closely bonded, where this scheduler is a software controller kind of a driver, which takes care of generating photons and then transfer it to a link layer. And the link layer also, it has a quantum memory management unit, MMU, where it takes care of all entanglement generation process, EGP, all entanglement generation process, it takes care. And then it goes for a higher layer. Once it is ready for flying, it's a flying qubit, and it sends to higher layers for a application level protocol. Then other end, it's a similar thing that it needs to capture and then perform the same action, and measurement is going to happen in other end. Next slide. So here, that's all pretty much about what internals of quantum networks. But here I just want to give a feel of what all the real-time quantum networks looks. So to my knowledge, almost approximately 40 QKD experiments are in field deployment. It's not only, it's across the globe, whatever literatures, to my knowledge, it's almost 40 QKD experiments are in field deployment. More than 100 experiments are in the laboratory level. So I've been fortunate to be associated with the Cambridge network for quite some time, and I would like to get chances how this actual implementation looks and how difficult it is. So here is a project names, and this is like a kind of a choosy. I don't want to go for all over all the 40 things. Some of the highlights of some particular project. These are like a major projects that's been carried out for deploying this field. Here is classification, network type and distance and country, maximum key rates and number of nodes, protocols and status. So I think Vaibhav mentioned this DARPA is the first quantum network which is conducted by United States by a Defense Research Institute of United States called DARPA. So this is, they've used both network type switching and trusted repeaters, and it's almost 29 kilometers, and the bit rate is very less, 400 bits per second, and 10 nodes being used. And the protocol that used is BB84. The network operators is still it's in operation. According to their report, it's still in operation in Washington DC and New York City. Another one is it's a European network, secure communication-based quantum cryptography. Is basically a European Union, which more than 10 countries been involved, particularly Russia and Switzerland are major stakeholders. It's around 33 kilometers. It could have able to achieve around greater than 1 kbps of data, secret keys, and 6 number of nodes being used, and different protocols being tried. here it is a combination of different protocols where they've been tried. So this is like now the European Union formed a consortium called Open Qkd, where they just trying to make it as some full-fledged quantum network systems across the globe. So all the standardizations according to this one. And the Cambridge network, it starts from the Cambridge, and it is a partner with many institutions. It's part of a quantum communication hub activity where the switching is being used 410. It's an ongoing project, and almost London to Cambridge is already been completed when I was there, and they were working on the up to Bristol. So it's according to the report in UK 2019, but it's an ongoing project. It can achieve only up to 1 Mbps of data. 3 nodes being used, and they are trying to apply PB84 based protocols. It's an ongoing project. And the Tokyo, Japan-based trusted repeaters. It's a collaboration project with the European Union, and it up to reaches 300 kbps, and 6 nodes being used. And these are the protocols there. And this is a completed project. So at this point of time, there is no status about current network status. So China has been conducted many experiments, field trial experiments. This is the latest one they were reported recently in 2021 in the paper. It's around 511 kilometers. It's a twin field. It's a new type of method that we tried. It is quite successful. And they used send and not send protocol. It's basically two users sending signals to a middle user. Then the middle user will try to apply some random choices, make the bit speed. So this is a twin field, and it looks more promising. And if you look at the key rates, it's more promising one. And another important thing is there is no trusted repeaters used here. So the only challenge in the repeater is it's not secure. We need to secure the repeaters. So whereas in this case, the twin field, there is no repeaters being used. Next slide, please. So what are the current practical challenges? So the main challenge, if you see, is if you look at the diagram here, I was trying to visualize in a triangle where quantum hardwares are not matured and classical network equipments are not ready or relevant to integrate. Another one is a telecom operators. So in this case, if you look at the real-time scenario, for example, if person A and B using a different system and different protocol, and other person is E using a different protocols, it's very hard to merge these two networks because everyone uses a different devices which are different manufacturers. It's very hard to integrate that. That's a first integration challenges for that classical network equipments and the telecom providers. And quantum hardware also, as Sonali mentioned, it is not matured enough to precisely measure these qubits and precisely generate a single photon sources. Another important thing is synchronization between the classical and quantum channel is another challenge. So, and these are like a major practical challenges. One is a high cost and expensive hardwares and lack of integrations because it's incompatible architecture, quantum hardware, since it's maturing, and the range limitations because we are facing a huge loss. If you see in the data rate, it's a huge loss during this in quantum channel. And there is no standards, at least at this point of time. People are working in it because if we don't follow the standards, we won't be able to create global wide networks. So another important challenge is practical security. So if you look at the diagram here, the quantum channel promises the keys or information is only safe in the quantum channel. If you take out the information from the quantum channel, the receiver end or transmitter end, after a measurement, it is no more a quantum holds a quantum property. It becomes a classical one. Then we need to apply classical security things in order to make it a secure. So this is another important practical challenge that we are facing in the last mile. Quantum is safe while it was in a channel. When it comes to a last mile key delivery and security, still it's a challenging for an experimentalists how to realize it end-to-end secure safe quantum keys. So with this, there are some suggestions or solutions I'd like to mention here, and this is becomes an opportunity to pursue in this direction. So first thing is a novel architecture, how this coexistence can happen, because the behavior of classical bits, as I mentioned, it is a logical process, as a quantum behavior or network is a physical, and how to make it a coexistence architecture and protocol and application services make it as a full-fledged quantum safe communication. And there are significant of research and engineering efforts is required to make it leveraging this quantum technology. And analyzing various tests how this networks performs when it in a quantum environment, the test beds needs to be created in order to test that. And moving towards that, as I mentioned in the functionality diagram, moving towards the quantum internet, we need to realize how to model the quantum internet in the various scenarios. So there are different metrics needs to be defined, and quantum control planes needs to be identified, and the relevant software stacks needs to be created. So these are like some of the opportunities where you can utilize, we can take a directions. Next slide, please. So other opportunities as well, the follow-up talk, we have a simulation framework. So how to simulate this before we go into the real field trial, and then apply some of the tools, security analysis, logical analysis tools to make a measurement on the functioning efficiency source, because we may not produce these such QKD boxes here at this point of time, but we need to evaluate those things with a certain consideration so that we can be ready for quantum safe environment. So there are some device independent and twin field systems, as I mentioned, it's under consideration, which all looks promising for future quantum safe communications. Next, please. There are some applications I would like to point out wherever the communications there, we can use this. So this was interesting application which was proposed by the Eleni Damayanti, where a bank can use prepare a quantum qubit states and store it in a qubit in a chip and then use it for a client. So the client can use machines and read these qubits and compare with this bank original qubits. So you cannot copy this qubit because according to the property. So this one is an interesting example which was proposed by Eleni in this conference. Which one? So kind of a summary is, yeah, so look forward. There are many challenges according to the distances and laws and imperfection of quantum device that need to be clarified to make a complete system, and standardization is required. And this standardization will motivate us to build a global level quantum network visions. And there are every country started national missions on quantum technology and trying to invest heavily on this space. And still there are a lot more research and engineering efforts need to be done. And here in India, there are workforce needs to be developed in these cutting edge technologies. With this, I would like to conclude. Maybe these are some of the references, and next please, next please. So I'd like to thank everyone for your patient listens, and I'd like to thank my mentors, and I'm happy to take some questions. Thank you.
Hello.
Yes, sir.
Yeah, Dr. Natarajan, you mentioned about standards. So,
Yes,
what are the SDOs or standard development organizations currently working on quantum standards? Any emerging standards you can highlight?
So there are some standards is already been progressed. So even we are reviewing certain things. These ISO based standards. European Telecommunication Unit standard.
Okay.
Yeah. So that is, it's under progress, and there was another consortium we formed to form a high-level standards for this, specifically for QKD networks.
Oh.
And even India also, there was an initiation to perform these kind of standards.
Oh.
I think Bureau of Indian Standards has started a new forum to develop, look at the international standards and also to see what Indian community can add to that.
Okay, I think there is an opportunity for India to contribute because it is an emerging area.
Yeah, you are right.
Hello.
Yes, sir.
Thanks for the organizers for arranging this wonderful presentation. Thank you very much. So my question is, you're talking about quantum internet. Do you mean it is specifically meant for global QKD kind of network, or it is a general purpose network where I can use it for sending files or YouTube, something like that?
Yes. So at this point of time, it is like a global kind of perspective. It's sending a secret information, the network also, but it requires some more functionality of transferring qubit as such in the network. Because so far we are make it as some kind of a teleportation mechanisms that we transfer these qubits. But the idea is we need to keep quantum memory or for a certain period of time. That so the most of the quantum internet works on the memory based. We required a certain memories to handle this quantum. But if it is feasible, then we definitely can do all this file transfer, everything through the quantum internet. But at this point of time, the focus is on generating a secret keys kind of thing.
Thank you.
Basically, if it integrates with the quantum computers, then it may be a full-fledged where you can just transfer all your all our communications becomes qubits, and quantum computer is the one handling the both ends. So we don't have any hurdles. Hopefully, in 2050 we are expecting.
Thank you very much. And another particular question I have.
Yeah.
What is the proof that these quantum things are completely safe and secure?
Great, sir. So the proof that is already demonstrated by a physicist, it cannot be unclonable, and it's according to the laws of physics. But yet to be explored in a logical sense, as a computer science perspective, that is a logical level of analysis required. How it is secure, as I mentioned, so last mile security is not guaranteed so far. So we need to adapt other mechanisms like other classical means, post-quantum kind of a cryptography. I can make it a hybrid system so that it is a completely secure environment. At this point of time, we have only a guarantee that the physics laws. The practical security is still as challenging.
Thank you. Thank you.
Any other question?
I do not know whether I am right or not. When it comes to the security, especially in the QKD kind of an environment, if it is Alice and Bob communication is happening, if EU looks at it, then it collapses. The measurement collapses. So there is that will not reach to the destination. Only thing is you lose that communication, but you would not be able to actually make something out of it. I don't know if I am right or wrong. Is it so? Yes. That way it assures the naturally quantum principles assures say high level security in that sense. Maybe you can make a comment on that.
Agreed, sir. Yes, sir. So it's basically identifying the ifs based on the qubit error rate, quantum bit error rate. So when the intruder inside the quantum channel, it reflects in terms of error rate. Both the ends error rate will become higher, so that users will notify that there is a intruder in between these process. So that's a proof. But we logically we need some certain things.
Yeah, thank you.
Over to you, Vice.
Thank you very much, sir. So you started with the basics on QKD side and went through the layered architecture of quantum networks, the practical difficulties, the practical implementations that have been done across the world, and the difficulties that we face in terms of implementing such networks. When means taking the research from lab to field, these are the things that we have to consider and we have to focus on. Engineering aspects become a separate focus area in itself. Thank you very much, sir. With that, we will move towards our QSIM demonstration, and for that we have Mr. Henry Sukumar from Syrac Bangalore. He works as joint director here at Syrac Bangalore, and he has a 15 years of experience in projects like Garuda, grid computing, cloud security, virtualization detection, and co-location attacks in public cloud infrastructure. His interests are in cybersecurity, cloud computing, web application development, and creative designs. I would like to request Henry sir to please take it forward.
Thank you very much, Vaibhav. Can you please confirm that if I'm audible?
Yes, sir. Yes, sir. We can hear you.
Okay.
Your
My
screen
is also visible.
Yeah.
Thank you very much for the introduction. And thanks to SETS and Dr. Natarajan for giving me the opportunity to speak about the QSIM. So my agenda is to give a demonstration of QSIM, but I thought I will give a very brief introduction about what is QSIM is all about, and who are the main players involved in this particular project, and how you can get access to QSIM. So with that, let me talk. So the QSIM is basically a GUI-based quantum simulator that has been integrated with IASC's in-house developed density matrix-based simulator. So it can be accessed over QCToolkit.in website. So I will take you through that demo in a short while. It's basically a platform for students and researchers to explore various quantum algorithms and see how well they work in idealized conditions, and help them prepare experiments to run on actual quantum hardware. So the most important thing is one can vary the imperfections and the connectivity in the simulator to figure out what design for the noisy quantum processor would produce the best result. So that is one of the important feature of this simulator, where you can fine-tune the various errors and it can help you to design and see how the algorithm works with imperfect quantum components, and it helps you to design an error-resilient system. The other important goal of this particular QSIM toolkit is that it's an important tool for an education purpose because programming a quantum processor is qualitatively different from the classical experience of computer programming, and so the opportunity and exposure provided by QSIM would be a very important role in developing the future expertise in this field. So the researchers and students can very well take advantage of QSIM to understand how their algorithms are going to work when there are a lot of noise in quantum computers. So if I talk about QSIM, I should definitely talk about the core behind the QSIM, which is IASC's ACA simulator. It's a software simulator for noisy quantum circuits. It's a density matrix simulator that has been written as a backend for IBM's Qkd. So if you have an experience with IBM Qkd, you will understand there are various modules in IBM Qkd, and AIR is one of the modules which allows you to have various simulator backends. So this DM simulator sits as one of the backend to the AIR module of IBM Qkd. And it follows a density matrix formalism because state vectors are ideal for describing the pure states of a closed quantum system, but they are really insufficient when you want to describe a mixed state that result from interaction of open quantum systems, right? So there are various error models that has been handled in the density matrix simulator. So it provides an excellent way to incorporate various environmental noises. For example, that quantum computer may suffer from many sources of error in the real world quantum computer. So it can be because of an imperfect state preparation, or because of an imperfect logic gate implementation, or it can be due to the disturbance to the data in the memory, or while measuring if there are any errors. So these are the error models that has been targeted in the density matrix, and this is straight away available in the QSIM as well. So with these improvisations, the simulation results, we expect the simulation results to look very close to what a noisy quantum processor would deliver. And one can test how well these algorithms are going to work in those imperfect quantum components. So these are the various features of QSIM. I will not be explaining this side because when I take you through the demo, I will talk about each of these features. So before that, I will tell you like QSIM has been offered in two different models. One is the Param-Shavak QSIM, which is a standalone quantum computer box. So you get a quantum computer box, a supercomputer box where you have a QSIM already loaded into it. And then there is a QSIM over the cloud. So that's what I'm talking about, QCToolkit.in website, which is offered over a cloud, and it has been integrated with a HPC infrastructure. For example, it has been integrated with Param Shakti resources, which is deployed in IIT Kharagpur. So before I give a demo, I would like to show a simple example. For example, this is a quantum circuit. It's a 2-qubit ripple adder program. So the idea here is you can just see my mouse where I'm highlighting that we are going to input two numbers, binary numbers, which can be 1, 0 and 0, 1. And then we try to extract that result with the help of measuring it. So this circuit, we will not get deep into the circuit, but it goes through 3 stages where we prepare the quantum states, we prepare the inputs over here, and then we perform an operation over there. And then finally, we perform a measurement to extract the output for the input that we have given. So with this, I will just share my browser. Hope you are able to see my browser. So this is the website of QSIM. So you can just go to QCToolkit.in website. So this is the landing page that basically explains about what is QSIM and how the users can benefit out of QSIM, and a brief introduction to the project and various stakeholders involved in this project. And this is the project which is in collaboration with Indian Institute of Science, Bangalore. They have developed the density matrix simulator, as I told, and then IIT Roorkee, who are contributing on the quantum algorithms, and which is funded by the METI. And these are various features. I will show you that in the workbench toolkit itself. And we try to have some kind of a knowledge base because we thought that there should be a lot of tutorials where it can help the users to understand what is QSIM is all about and how you can use the QSIM. And if you have any queries and if you want to access QSIM, you have to just shoot a mail to qcworkbench@syrac.in with the information that is presented over here. It's a basic profile of yourself. You can just write it to us, qcworkbench@syrac.in. Currently, the QSIM is available only through this method because we have integrated with HPC resource, but we still have a limitation with the HPC resources that is available in IIT Kharagpur, which is heavily used by many users in IIT Kharagpur as well. So we are giving based on the request of the users. And there is an FAQ page where I have tried to answer most of the questions that you might come to a mind when you try to use QSIM. So this FAQ will be really helpful when you have doubts on what is the simulator and what is the number of qubits that are supported. Currently, the QSIM supports up to 12 qubits, and you can go up to 13, but we have limited with 12 here. And we are working on the next version to support more number of qubits and expand the HPC resources that we have. So now let me take you to the workbench layout. So you can just once you get the login details, you can click on Launch Workbench. It takes a couple of seconds to load. And this is basically the layout of the workbench. So I will straight away take you through the tour of this layout. So you can see that this is the Python code editor where you can start writing your Qkd program. So if you are well versed with Qkd Python programming, then you can start writing the program over the editor. And this is like any other IDE where you get all the facilities of syntax highlighting, errors, and then searching and replacing various keywords like that. And there are shortcuts that are available over here. You can just explore these things when you access the toolkit. And then the most important part is you write a program, but you want to visualize how the circuit has been generated, and that happens instantly when you write a particular gate line and give an enter over there. It triggers an instant circuit module and your circuit gets updated over here, and it takes few seconds to update. The next important part of QSIM is the noise parameters. This is very important part where that's the specialty of the density matrix simulator developed by IISc. So there are various noise parameters that I will show you a little while. And then you can plot the histograms to see how your program performed with noise and without noise. And you can partition the circuit and see how the various gates has been transformed or transpiled by the our simulator. And once you have your code ready, you can just hit on this run button and the job directly submits to the Paramsakti HPC resource at the backend, and you are presented with the job ID, which you can use to track the status, fetch the output, and export those details as well. So yes, simulations, so there are various other options which I will explain. So basically this is the editor. This is like any other IDE that you see. So you start typing and you get the options listed over here, and then you just start printing like this. So this is the very important part of the QSIM, where there are various noise models that are by default displayed and default values have been mentioned. And you can just click on this tab and start customizing these values. For example, I can set a rotation error, which is a gate error. And for C0 kind of a gates, you get set a TSP error model. So you can just click on this and change various error parameters. And then you can also enable plot. And you can also partition it so that you see how the circuit has been partitioned, how it has been transpiled by the VM simulator. And you can see the code where this is the backend. And as I told, DM simulator has been written as the backend to the AIR module of Qkd. And this was released in 2019. So that time there was a basic AIR module. So it works very well with the basic AIR module. And IISc team is working on to incorporate this into the next version of AIR module itself. And here we execute the program and we fetch the density matrix result over here. So before that, I will just take you to the example folder where we have various examples and algorithms that has been ported. And thanks to IIT Roorkee, who have given these algorithms for us to be ported into the QSIM. And here one of the example is the that we saw in the presentation. So here you can see this is the code of the 2-qubit ripple adder. Though we have 7 qubits declared over here, but we are going to perform operations only with 2 inputs and try to get an output that we wanted to get. And then here you can see the most important part is this program is going to compare the output with and without noise. So there is an options variable which does not take any noise, and there is an option variable which takes noise. And you can see the value of 1.0, it's a floating number which represents it is errorless. And when you decrease it, you are going to set an error level, okay? So for example, you can see a decay factor which has 0.09998. So that is the error parameter that we have set over here. And as I told, these are the various gates that has been added. And if you go here, there is an important line where we try to do a measure, and that has been denoted as a red triangle on the getter. So this is the code editor getter. So you can just right click over here and try to add various measurements. Currently QSIM supports a single qubit measurement. So you can choose on which basis you want to do the measurement, X, Y, Z, or N arbitrary base. So when you do that, you can see then this is an ensemble. So you go over here, you just select any of the ensemble measurement, maybe is the basis, add measurement. You can see that ensemble measurement gets added over here. And you will also see there will be an ensemble probability that is added to the line as well. So this is how you can add various measurements. There is also an expectation measurement, which is something similar to the ensemble measurement, but it requires Pauli string as the input, which should be equal to the number of qubits that we are presenting over here. And here I will show you that yes, here. So we are going to execute this program without noise and as well as with noise, and we are going to store it onto a variable. And then finally, we will distribute the ensemble probability output. So once the code is ready, you can just click on this run button, and it takes a couple of seconds because it has to connect to the HPC resource at the back end, the param-sakti, which is located in IIT. And you will get a job ID which is presented over here. And you can click on the simulation tab to see whether the job has been submitted. So here you can just click on this job ID, and you can see that it has been queued. And this is the bad time to give a demo because IIT Roorkee, the labs are heavily utilized during 6 to 9:30. So that's what I was told. So anyway, the job has been submitted and it is queued. So it should take a couple of seconds before, couple of minutes before it is getting scheduled. So let's go back to the simulation page where I was prepared with one output. So let me click on this output. So here you can see the same code that I was showing in the screen. I had submitted just a few minutes before the presentation. And you can see there is a blue bar which represents the output. So we try to add 2 plus 1 and we expected a result 3. And you can see when there is no error, you can see the blue bar predicts a probability of 1. And where is an error? For example, we added an error in the DK parameter, which is very minute, but even that error can disturb the output. And you can see the probability of getting 3 has been less, and then it has been distributed across this. So now if you keep on modifying or changing various error parameters, you will see a huge difference in the output. So in this way, the users can experiment with various quantum algorithms and try to see how they behave when there is an error in the quantum computer. So this is the basic example, and you can fetch your outputs over here, and then the code that you use for submitting and the circuit that we submitted as well. And you can also export this if you want to do it for any documentation paper, or if you're writing any publishing any paper, you can use these results onto a paper by exporting this. And you can also click to resubmit this. So you want to experiment by adding some more error parameters, you can just resubmit this program by modifying the DK parameter. So you can add some more fine tuning to the errors and see how well it works with the simulator. So that's it about the demonstration of QSIM. So if you want to access QSIM, all you need to do is just send a mail to qcworkbench@syrac.in, and I will be sending a mail with the account details, and you can start using it. And of course, I welcome any feedback on this. The tool is being continuously improved, and the next version we expect to support more number of qubits and add more number of HPC resources as well. And as I told you, it supports currently single qubit measurement, expectation and ensemble measurement, and we are also working out on the bell basis measurement and integrating this tool with the Jupyter notebook as well. And this DM simulator is generally is very memory intensive, so we are working on optimizing the memory and then trying to scale by parallelizing it and making it to work on GPU as well. So that should also be available in the next version as well. So as I told, it supports 12 qubits. So there was a question pinged to me now. So it supports 12 qubits in the version 1.0. So that's it. If you have any questions, I can answer. Hope my presentation was not interrupted due to any internet issue or anything like that. If you have any questions, I can answer.
No, it was smooth, sir. No issue.
Okay, yeah.
Request if people have.
Yes, if someone.
Satish Kumar, I can unmute you and you can. Please go ahead, sir. Please ask a query.
Yes, sir.
Satish Kumar. Yeah.
Sir, is it a free tool to download and work, or is it supposed to be done through the simulator which is provided by the Indian Technology?
Okay, thanks for asking this question, and I forgot to tell about that. As of now, the QSIM cloud version is free. You can just send a mail and you get an account and you can start using it. And you can also download the IAC simulator. So in one of my slides, I have mentioned the a paper publication by IAC where they have a GitHub repository where you can download the DM simulator and just run it on your Jupyter notebooks, and you can do that as well.
Okay, thank you, sir.
Thank you very much. Is there any other questions? If you don't get a question right now, you can very well mail me qcworkbench@syrac.in and I will respond to that. Thank you very much. Thanks to Syrac sir and Dr. Natarajan for giving me the opportunity to speak about QC. Thank you, Vaibhav. Thank you.
Thank you very much, sir, for the insightful demonstration. With this, we reached the closure of today's webinar on quantum networks, realities and opportunities, organized by Net India, SETS, and CDAC. I would like to thank Dr. Syrac at SETS, Chennai, Dr. Sudarshan at CDAC, Bangalore, and Dr. Pavintan at Net India for giving us this opportunity to organize this webinar, to have these insightful, and the real benefit that came out of this talk was the practical implementation aspects. When we take these things to field, what all things we have to take care of, and what are the challenges that will come forward. Right from starting from the first talk where Professor Urdusi had laid out the foundation of QKD and quantum communication, to Dr. Sonali, who pointed out a particular use case. If we are doing satellite-based QKD, when we take it, when we do it like that, what are the issues, the miniaturization aspects, the cloud cover aspects, etc. And then Dr. Natarajan, who pointed out the layered architecture of quantum networks, what are the field deployments, and what challenges we encounter when we do such deployments. So I would like to thank all the speakers for taking out the time to share their thoughts with us, share their experience with us, and it has been a wonderful experience to hear to all the wonderful speakers. Thank you very much. I see.
From that side, I would like to thank everyone, especially Dr. Pavantan, having mooted the idea of conducting this in a very short time. And
thank you, sir. Thanks for the opportunity. Yeah. Without your support, this wouldn't have been possible.
And Dr. Sudarshan, always open to all technical events, and for him also and his team, readily agreeing, especially Mr. Henry coming and explaining to us QSIM added a value to this. And also Vaibhav comparing throughout and taking right from the beginning, giving an overview and till the end. He has done a good job. And I have to thank Dr. Natarajan, who is an inspiration for me in the quantum security area from SETS. And in fact, in the introductory things, I forgot to tell the activities that we do. The metropolitan area is the present quantum key distribution research happening everywhere, and a lot of efforts are going on. This is the first project funded by METI between CDAC and SETS and IIT Madras. IIT Madras, Dr. Anil Prabhakar is chief investigator, and all other teams are working under his guidance, and we're very happy to be there. And ERNET is also becoming part of it, along with NIC, to be part of this program. We're looking for the large-scale quantum networks in due course of time, with the same team and ERNET and NIC being part of it. So, in addition to that, we are parallelly, whether we have a quantum computer or not, to take care of our things. Post-quantum cryptography is an important area. That is a quantum resilient, cryptography also we're working on. So these are some activities. People who are interested can visit SETS website to see more details of our cybersecurity activities. thank you one and all for being with us patiently. It's a evening time, little odd, but for the convenience of the speakers, these timings were selected, especially the European speaker. I think all the speakers gave what best they can give and made us, quite brought to some level of knowledge in this area. I take once again this opportunity to thank everyone who was part of it, and I thank the organizer, Microsoft Teams, our coordinator, Vaishnavi here from our center, who has quickly provided the platform and managed this event. Thank you all. Thank you all.
Thank you. Thank you, sir. Thanks, everyone.
Thank you very much, sir. I think with this we will conclude.
I thank some senior members, Dr. Ananda Mohan, Mr. Pichaya, Mr. Gopinath, Dr. Sivakumar, and many other distinguished members from various organizations who have joined this program. Thank you all, sir. Maybe the coordinators and organizers can come on the video to take a photo.
Hello, sir.
All left, is it? Pichaya sir is there. Dr. Sudarshan. I think. Most of the people probably muted and the video also switched off. Nice, Vaibhav. It's pleasant comparing from your end. Huh? Dr. Shiv? Dr. Shiv, you are there? Okay. So let's formally close. Vaibhav, shall we close?
Yes, yes, sir. So I was actually talking to Sudarshan, sir. He is in another call, I think.
Yeah.
A meeting, so.
Natural. That's natural. Yeah. Okay. Have a great time and
Thank you very much, sir. Thank you for the opportunity. Thank you.
Yeah. Welcome.
Thank you.
Have a great time.
Thank you for all to all.
Thank you very much.